Hi everyone, thanks for coming, dragging yourselves out of bed so early. I decided to reduce the amount of stuff that I'm going to present, and I figured that I'd rather everyone understand what I'm saying and say less things and say a lot of things and not understand. So that means there should be a little bit of time for discussion, so feel free to interrupt me if I've lost you at a certain point. Yeah, or something's particularly interesting that you just can't wait until the end to talk about. Very happy to chat. Yeah, let's get into it. So my work is trying to understand how the brain understands speech. So in other words, how is it able to take the auditory signal of speech and from that derive a conceptual understanding of what it is that's being said. And all of my work is trying to understand this system, the brain, that's able to map from sounds to meaning. And I'm sure you can appreciate this is not a small, easy thing to solve. I'm never going to solve this in my career, but hopefully I could make some progress towards answering this. And to try and make sure I am making progress, I organize my research program around 3 sub-questions. So the first is, in mapping from sound to meaning, what are the representations that the brain generates in order to form kind of a representational bridge from sound to meaning? And to be concrete, by representation, I mean things like maybe a representation of the syllables that someone is saying, or maybe a cochlear representation of the auditory signal, or maybe something more abstract, like the actual meaning of the words that are being said. Second, we need to know the operations that are in place which generate and manipulate those representations. So, for example, some examples of operations might be filtering of the input signal, or maybe performing a non-linear transformation. So maybe you're going from something which is linear on the input side to derive a discrete category, that this is, say, a P sound and not a B sound, for instance. Oh yeah, this was, and other computations which might occur. So yeah, this is filtering, nonlinearity, summation, and others. Yeah, and I think it's actually kind of interesting to point out that we know a lot more about the representation side than we know about the operation side. I'm not going to go into kind of too much detail about that, but it's much harder to figure out what computations, what operations the brain is applying than figuring out what the brain is representing at any given moment. And yeah, so there are a lot of kind of question marks on the operation side. And the final part of this, I kind of term as information flow. So we need to know, for example, the order with which these different representations get generated and how information is passed between different neural ensembles in order to lead to the results of output. So examples of information flow might be feed forward flow, or feedback, or recurrent connections. These I would all kind of partition under the information flow part. Okay, and just to give you a little bit more insight into, oh yeah, please.
In your diagram, you showed an ordinary or a very nice sequence of operations. How about branching or parallel?
Yeah, and we'll see some examples. Obviously, this is a very nice schematic that never is going to actually be the case in real life. And I'll show some results where a lot of things are happening in parallel. And that's kind of one of the main take homes of my work in general.
Okay.
Is, yeah, there's a lot of parallel processing. Mm-hmm.
Yeah, and you probably had this on the previous slide. I just wanted to better understand your definition of input and output in the system.
Yeah, so the input would be just the fluctuation in sound pressure. And then output is tricky to define. I like to say it's comprehension, but comprehension of itself is really difficult to define. So But I think we all kind of have an intuitive idea of what comprehension were to mean. I guess maybe another way of putting it is the output after you kind of combine all of the information you possibly can to extract everything you can from that acoustic signal. But it's a good point that the output actually is not so straightforward. Yeah. All right, so just briefly kind of introducing myself a little bit more. So I work at the intersection between a few different disciplines, between neuroscience, data science, and cognitive science / linguistics. And I really think that this is important for understanding speech comprehension in the brain. Linguistics is super helpful for generating hypotheses of representational spaces, for example. And data science is really helpful both for analyzing the data and for essentially coming up with computational models of how these different processes might occur. You'll see also that I try to use naturalistic paradigms. So this is the case of people listening to, say, audiobooks or podcasts, rather than being bombarded with like one word and then silence and another word and then silence. I'm trying to make this as ecologically valid as possible. Yeah, exactly. I find my badagaga days, but yeah, at least I'm trying to move more in this direction. And yeah, big supporter of open science. And you'll see today as well that I've had the opportunity to work with neural recording techniques at very different spatial scales. So I'm going to talk today about some of my MEG work, which is recording whole brain activity non-invasively. And I'll also present some of the work on kind of the other side of the continuum, which is using neuropixels probes. And these are a method of recording individual neurons. And I'll show some human data of neuronal spiking in auditory regions as well. Okay, so today there are two projects that I want to share with you. The one is trying to understand some of the computations in play to support speech sequence processing. As I said, this is been given much less kind of attention than the representational component. And then, as I said, because we have access to individual neurons, let's look at the implementational level to see how these different speech features actually are implemented at the level of single cells. Yeah.
So does speech sequence involve also the binding effects, where you combine different sounds, sequence of sounds as one unit?
Yeah, right. I'll remember that and I'll address that when I show you the data. Mm-hmm.
In the interest of helping to blow up your talk before slide 10.
Yeah.
So today we're talking about speech processing.
Right.
I'm wondering if you have strong theories or awareness or understanding of how speech processing differs from all other forms of acoustic processing regardless.
Yeah, nice question. So some of the processes are shared with general auditory processing. I was actually having a nice chat with Claire, who isn't here, but we were saying about kind of replicating some of my studies in music and seeing this is another acoustic stimulus that humans care about as well, and seeing how kind of shared these processes are. So in this first study, what I'll show you, I think that there's going to be a lot shared with general auditory processing. There's some data where it differs, and I think that's actually a really interesting kind of question, is where that divergent point exists and what level of the language hierarchy. Is it very specific to language and something you would only see in humans? We're good? Cool. Okay, so just to make sure we're all on the same page of basics of speech representation. So this is a spectrogram of someone saying, well, his long tail swished to the rhythm of his thoughts. So you have frequency on the y-axis and time on the x-axis. And it's believed that one of the first operations the brain applies to this continuous signal is to discretize it relative to what are called phonetic features. So we're doing a quick linguistics 101 now, but don't worry. So this chart shows you all of the consonants that can be identified across the world's languages. And each consonant is defined relative to 3 phonetic features. So it's a kind of 3-dimensional representation. You have place of articulation. That means where are the tongue, teeth, and lips positioned in the mouth as the sound is made. You have manner of articulation. That means how is sound allowed to pass through the mouth as the sound is made. So maybe just to be concrete, you can contrast, for example, T to S. They're actually both articulated in the same place in the mouth, but the T involves stopping the airflow and then releasing it, and the S is just the constant release of airflow. Nice. Okay, cool. And then the final thing is voicing, and this means do the vocal cords vibrate during the initial articulation of the sound or not. So okay, everyone put your hands on your voice box and make a S and a V. So so the only difference between those two, very nice guys. The only difference between those sounds, as I think you all appreciated, is the vocal cords vibrate or they don't vibrate. So this is the other dimension. Okay, and these 3 dimensions of phonetics, so these are called phonetic features, have been shown to be encoded in neural activity when you're listening to people speak. What's interesting though, I should say, and where does this happen? This happens in this gyrus here, which is called superior temporal gyrus. I think I'm only talking about this brain region throughout the talk. And this has been implicated a lot in speech processing. And different populations of neurons in this gyrus seem to respond selectively to these different phonetic features.
So
Yeah.
How is that related to the models?
Yeah, right. So let's not go there.
Okay.
But your point's well taken. The feature space I just described is describing how the sounds are made, not how the sounds are perceived. It turns out that the way the sounds are made correlates very well with how they are perceived. Let's not go into why. Yeah.
How like orthogonal spectrums and poorly are each of these features? Like I know some are close to others, but on average are they pretty orthogonal?
So it's a good point. So the manner of articulation, for example, so like the T versus S is a very clear acoustic distinction. Where the sounds are articulated in the mouth is very subtle. And this, so some of them are more kind of separable than others in the feature space. And it tracks the kind of mistakes we make when we're listening to people talk as well. You're much more likely to confuse that someone, where the sound was articulated versus the sound of it. Okay, so let me present a little puzzle to you, which is kind of the segue into this first study. So the brain processes these phonetic features, and each of these sounds on average is about 100 milliseconds. So you can imagine a world where the brain processes these phonetic features for the duration of that sound, and then continues to process the features of the next sound, and then the next sound. So the features are only going to be processed for about 100 milliseconds in time, and then that's discarded because you need to process the next sound in the sequence. But what I found in my previous study was if you're looking at, say, a very simple distinction between P and B, this distinction is not only present for the duration of the sound. You can decode this from neural activity for about like half a second. so way into the processing of the subsequent sounds. And the purpose of this prior work was to kind of show the advantages that that might have to the processing system. So let's say that you're hearing a sound that's pretty ambiguous. You're not sure if it was a P or a B. Well, if you're patient and you just wait for the word to finish, that will disambiguate the identity of that sound for you. So if the word is parakeet, you know it was a P. And if it was barricade, then you know it was a B. And so this information maintenance has some advantages to it, but it also raises some kind of puzzling questions. So yeah.
Posing that the word is a unit, not a syllable, or
I'm not making any claims about unit size. And yeah, I mean, in that prior study and in studies I've done, it actually seems like the information is maintained until a word boundary, slash maintained until the certainty about what the word is going to be reaches a confidence threshold. Yeah, but again, I'm not going to talk about that too much. Okay, so why is this puzzling? If I say a very simple word like hello, it's made up of 4 sounds. So let's say you're hearing the first sound, huh, and it lasts for 100 milliseconds, but you're processing it for, let's say, 400 milliseconds. And as I told you, it's the populations in this brain area that process that sound. And then you hear the next sound, while the first sound is still being processed. And you hear the next sound, while the 2 previous are still being processed, and you hear the next sound while all of them are being processed. So by the time you're hearing this last sound of the word, at least theoretically, all of the sounds of the word are all being processed by the same set of neural populations in this brain area. And this leads to two kind of obvious questions. The first is, how does the brain not get confused if it's processing all of these sounds at the same time in the same part of cortex? And second, how does it correctly figure out the order with which those sounds came in? Because that's going to be critical to figuring out what the word actually is. There's plenty of words that are made up of the same phonetic elements, but the order with which they're positioned will tell you it's pest and not pests, for example. Okay. So there's a specific hypothesis that I wanted to test here, which is, let's say that rather than the same set of neural populations are processing the sound the entire 400 milliseconds, maybe something different happens. Maybe it's all within this brain area, pituitary gyrus, but there's an initial set of population that then pass the information to a different set of population. And so the information gets routed to different neural populations as a function of time. And so what that would mean is that even though it's all broadly in the same brain area, it's never the same neural ensemble, which is trying to process multiple sounds simultaneously. So that's the hypothesis we want to test here. Is everyone on board with what I just said?
Yeah. Is it the same as feed forward versus recurrent?
Yeah, you could see it like that. Yeah. So feed forward being that you're moving it around different populations, recurrent being it's local and just maintained in the same set. You could see it like that.
Well, you know, everybody who does any kind of CNN processing, but it's going to think that way.
Yeah. Yeah. Okay. All right, so let's get to the data set. So this is 21 native English participants, and they listened to 2 hours of short stories while I recorded their brain activity with magnetoencephalography energy. So this is, as I mentioned, this is a device that can measure the magnetic field created by electrical impulse in the brain non-invasively. And that 2 hours of listening corresponds to responses around 40,000 phonemes per participant. So we have a pretty reasonable amount of data here. I'm going to play you a segment of one of the stories now, so you can get a sense of what it was that people were listening to. You'll notice that I chose to use a synthesized voice. If I was to do this study again, I probably wouldn't make that decision, but that's the decision I made at that point in time. But I think for the purposes of what I'm looking at, I think that my kind of conclusions still hold. So let's listen to a piece of it.
So there's no articulation here.
Was wearing a Shinternu jacket and snow boots, but he had on a Hawaiian shirt underneath and khaki shorts of all things. His tan was obviously deep and old, but it looked like a work tan, not the kind you get at the beach. His hands were thin and huge-knuckled with obvious calluses.
Okay.
So one of these tragedy books about that we really like to read sometimes. I hope. Come on, guys.
Okay, yeah, I'll give you the benefit of the doubt of why you thought that. Yeah, no, these are 4 short stories that were already annotated for the syntactic structure, which was a big win. So I didn't have to go and do that or get some undergrad army to code that up for me. Yeah, this particular story is about two guys that went to undergrad together, and then they meet up 20 years later. And the one has found a way to transport himself to wherever he wants in the world. So obviously they go and try and rob a bank. And then the one guy kills the other one and steals his gold. Yeah.
Audience is paying like broker, did you like mix the voice and like make the technical figurative like?
Yeah, so I had the text of the stories only, and then I used the Mac OS system actually to synthesize the voices. And there's I used 3 different voices and varied the speech rate slightly to try and inject a little bit of acoustic variability. Yeah.
So what should we expect to see from here?
Okay. Let's see. Okay, so what do we do with all of this? I should say, I released this data publicly, and so I think this is super valuable set of data for so please. Okay, cool. So what's the sorry?
Is there a bunch of these mega electrodes?
No, there's no name. It's
Magnetic or second?
Yeah, magnetic. Yeah, so the superconducting to
Yeah, how many of them?
There's 208 channels.
208, wow.
I don't know why I always do this whenever I
Yeah. Like a toilet in your head.
yeah, exactly. That's probably just correct. Okay, so we have this. Okay, so we have this continuous speech signal, which I've annotated the timing and the identity of all of the speech sounds. And I derive from that the phonetic features, just like I described. So we have voicing, manner, place of articulation, and it's these features that I'm going to decode from the neural activity that people listen to the speech.
Well, why do you do this as a function of putting in position in the word?
Right, so I do that because I want to understand how the sequence is processed. So
Oh, I see.
yeah, so it'll become clear in a moment. So let me just
One more question, how do you align the voice with the EEG signals? There could be some delays, how do you actually align them?
yeah, so there's a nice automatic tool called the Gentle Aligner, which I provide it with the sound file and the text transcription, and it does a pretty good job of outputting the timing of all of the phonemes. It's yeah, and I went and kind of tested random subsets, and it was pretty good.
And I have a question for the audience. So is there a reason why you're doing MEG for this sample, for this time study versus ECOG or something else?
I mean, ECOG would be great, but there's limited access to ECOG
For
data.
EEG, let's say.
I mean, MEG has excellent temporal resolution
Okay.
and better spatial resolution than EEG, and not just is the resolution better, but there's also more information contained in those signals, about twice in my experience.
Okay.
Yes, you have.
I wonder with ECOG versus, let's say, MEG or EEG. With ECOG, if you don't know where these things are happening, you're kind of taking a shot in the dark and you
Yeah.
record locally.
Right.
It's like doing single cells with the,
Yeah.
whereas with the MEG, you get a bigger picture.
For the whole
And then you can go in and
and also with kind of temporary resolution, but that was the question.
Yeah. Okay, so the way the analysis works is I have, as I said, all of these 40,000 phonemes, and I'm going to fit a classifier relative to when that phoneme began. So I'm going to fit one classifier at time 0, a different classifier at t+1, a different classifier at t+3, etc., to essentially have an array of classifiers, each one that's found the optimal topography to distinguish, say, a voice that is a voiceless sound at that delay relative to when the sound began. And I fit that classifier on all of the sounds within cross-validation, but regardless of where that sound occurred in the word. So I don't care about that for the training portion. And then for the testing, I'm going to take each of those classifiers at different delays and evaluate them also at different delays relative to where the phoneme began. But critically, I am going to split this up depending on where the sound occurred in the word, so that I can separately decode each element of the sequence. So the outcome of all of this is going to be kind of two-dimensional decoding accuracy plot, where you have delay relative to when the sound began on the y-axis and time relative to where you are in the word on the x-axis. Okay, and I think it all becomes a bit clearer when you actually see the data.
But not in place, it's not a location for you. Where is there a location in this? Or
Location in time, you mean?
No, location in space.
We'll get to that.
Okay.
Now we're just interested in the time courses,
Okay.
taking all of the senses together.
Okay.
Yeah. Okay, so the idea here is if it's the same neural populations that process this down continuously over time, i.e. it's a more recurrent type process, the classifier I fit earlier in time will do just as well late in time because it's the same neural population throughout the processing time course. If, however, it's more like a feed-forward process where the information is being routed to different neural populations, the classifier earlier in time won't do very well at the neural response later in time because the neural pattern has changed at that point. So, yeah, so we're essentially contrasting kind of diagonal type shape here to a more square type shape. Okay. So here is a contour plot in that two-dimensional decoding space that I mentioned for decoding just the properties of the first phoneme of the word.
What
So
P1 mean?
phoneme 1.
Okay.
So this is the onset of the words. So what you can read from this is that you start to be able to decode the features of this sound at about 100 milliseconds after that sound began. And this matches very well with previous work. And you continue to be able to decode this feature until about 450 milliseconds. So this also kind of proves the longevity of phonetic encoding.
So from a functional perspective, because I was
Yeah.
an engineer assistant, should we interpret this as we need a context of about 350 milliseconds to capture the essence of this a context? I mean, you need.
Like the previous sounds.
Yeah.
I mean, this in theory would happen even if there was just silence preceding
Oh,
this is just for how long that information is still present in the brain responses.
I see.
And so is this a trajectory or the whole region when you can find the information? How do you read this line?
You mean like this line?
The squiggly one. The
And
red.
squiggly, yeah. So I mean, I interpret it as a trajectory. The fact that it is let me get back to you in just 1 second. So what's important here is the fact that even though the overall decoding time is very long, any given pattern of activity over the MEG sensors is only informative for actually a pretty short period of time. So 80 milliseconds. So in practice, what that means is that the neural pattern here is different here and different here and different here. All of them are informative, but the actual ensemble is different as a function of time.
Is there some acausal information as well? I'm trying to interpret.
Yeah. So there's this little appendage, which you'll see when I reveal all of the data. There's only there for the first phoneme of the word. I really want to follow this up with future work, but what this tells you is you can decode the properties of this sound before the sound happens.
Given, do you know, like the statistical structure of this example, would that phoneme highly likely, given its context?
I mean, this is about 7,000 phonemes together.
Okay.
So the likelihood is gonna vary. I did try. Did I do that? I think I did try and split it up into word expectancy, and I think this was present in both cases, but I didn't look at it super carefully. But my best guess is that this would scale with how much you can predict what the next word is going to be.
Yeah, there's probably a lot of mutual information between what you just heard and the first phoneme.
Yeah, right.
You said something which is just in the past. You could predict before you even hear the sound.
Yeah, that's what this kind of shows. So the
Which is, yeah, fascinating.
yeah, it's really cool. Yeah, and it's only there for this first sound. So I'm actually I wonder if part of the way by which you predict the upcoming word is by predicting the first sound, because once you know what the first sound is, the entropy over the following sounds is super reduced. So it'd be a pretty efficient way of you kind of anchor yourself with the first word, and then the sequence thereafter is much more predictable.
So did you suggest that you have a forward predictive model?
Yeah. And I think this would be a great thing to follow up.
Okay.
Yeah.
So by first word, do you need the first word after a silence of the sentence, or the first word just in a sentence if there's like individual words, just the first sound of each word?
Yeah, I mean, most of this is in the context of continuous speech, so there will be no silence preceding it in most cases. We have about 500 sentences, so roughly about 500 of the 7,000 of those instances would have some silence before them, but it's not the majority.
So this sound is like the first sound of every word?
Yeah, that's right.
Okay.
Yeah. You have
just want to comment about the predictive. I mean, totally true, of course, that prediction could play a big role in this, but also the definition of an onset of a phoneme is not always obvious.
Yeah.
So many phonemes require, for example, to say T,
Yeah.
you have to place your tongue in a particular way. And as you anticipate, you're going to need to say T, you begin that move.
Like the co-articulation, given the sounds.
Like co-articulation, yeah.
Yeah,
It includes prior to T,
right.
for example.
But that's very big, so it doesn't matter particularly.
No, I think the synthesizes co-articulation as well.
I see.
Yeah.
Also, the spectrum of the speech, it doesn't matter synthetic or not. If you're going to say the T, that's what spectrogram looks like.
Yeah.
Prior to it, things begin to.
I think what's critical here, though, is that, I mean, this particular anticipatory effect, let's call it, is only there for the first sound, and co-articulation is both within and across word boundaries.
Yeah.
So, okay.
So what she had said, are you connecting with motor system?
Yeah, I know. Even she doesn't know the difference.
Okay, so I think I've convinced you that we have this evolving of neural populations, a function of time. And that's not just something special that happens at the first phoneme, it's there at the second phoneme of the words, the third, the fourth, the fifth, as well as the last phoneme of the previous word, working backwards as well.
Oh, this is really
So yeah, all phoneme positions in the sequence, they're this dynamic coding scheme. And I realized that this actually comes with it a number of pretty cool processing advantages. So if I highlight just a kind of horizontal slice of this plot, you can see that there's virtually no overlap between the kind of representation of one phoneme and its neighbor. So they're never kind of co-inhabiting the same neural pattern at the same time. Because by the time the next sounds come in, enough time has occurred that the previous sound has kind of moved over to a different station. And so I think that this kind of lack of representational overlap partly solves that puzzle that I presented to you of how the brain is not getting confused about processing multiple sounds at the same time, is that they don't have to kind of compete over the same neural ensembles at the same time. Similarly, if I just focus on a vertical slice, so this is half a second into the word, I kind of confirm again what we thought, that you can decode from one instantaneous time step the history of the previous 40 sounds that entered into the ear. But because this is a evolving trajectory over space, not only can I tell you what the identity of those sounds were, I can also tell you the relative order with which they entered into the ear by virtue of what neural ensemble is responsible for processing that sound at that moment in time. Does that make sense? So, because more time has evolved since the first sound came in, this has moved more over space. Because, as I said, this seems to have a lot of advantages. I don't need an explicit position coding scheme. That comes for free by virtue of having this evolutionary code. So I think that's really cool. I only have like 20-15 minutes left, and I want to make sure we get to the neuropixel stuff.
Well, this is the spatial.
This is the spatial thing. So the main point here is in the schematic and how I set this up, I can try to set it up in the simplest way possible with kind of a gradient from, say, posterior to anterior across the gyrus. That you're kind of like moving nicely in one direction. That doesn't at all seem to be what's happening. So this looks like a spaghetti mess, but that's the claim. That it's rather than having a clean transposition from like back to forward, instead I think what's happening is you're just adjusting the relative weights of the entire population. And I think that's sufficient to kind of move the representation of the different portions of this space such that they don't overlap. But it doesn't necessarily mean that neuron A then kind of like turns off and passes it to neuron B, but rather it's this more population code across the whole gyrus.
Yeah, so I mean the color coding suggests for each one of those vertical columns that there is an evolution in space over time. But if we look kind of across this, would you say it's more heterogeneous, that relationship between space and time? Or you mean like different features have different like trajectories? Yeah, or because with MEG you get fairly good sampling, but you're still aggregating the activity of many neurons. Right. Yeah, like 100,000 probably. Yeah, so there may be a bias. So maybe for place, you're seeing a spatial bias, but it's all mixed across space in reality. I'm just interested in your thoughts, and maybe the neuropixel section will. Yeah, I mean, I think I can't make too many claims on the spatial stuff with the MEG data. I guess I'll show you I did do like a quick and dirty analysis on some ECOG data that I had. So the box is the extent of the grid, of an electrical topography grid. And I'm going to play you a little movie. I think this is for voicing.
The size and the intensity of the color is the beta coefficient of decoding voice versus non-voice. So I'll just play this. So
is he quote from the same person that you?
no, this was, I moved from my PhD to my postdoc, and I was like, oh, let's have a little look.
Okay.
Yeah, so I mean, what I see here, at least, this is not a very systematic, I want to do like a dedicated study, but what you can see is one, that this information is there for a long period of time in this different modality, but two, you just see it kind of like rumbles in superior temporal gyrus for a long period of time. And so I think that that is essentially what's being reflected in the MEG data, just this adjusting of weights over the neurons over time. Okay, so I want to make sure that we get to the neuropixels. So I've done work across the whole hierarchy of language, and we're going to skip this. It's very cool. It's beautiful stuff. But now I want to make sure that I show you the neuropixels, because I think that this is pretty nice. So here we're looking at the same brain area, the superior temporal gyrus. And as I said, this has been implicated a lot in speech processing. It's been shown to process these different phonetic features, as well as some other properties of speech, like quality and the intensity of the speech. But what we have had no access to up until this point is how this information is actually organized as a function of cortical depth. So we have access to kind of the surface XY coordinates, and we can say on the surface, it seems that this population is encoding this, but how is that actually played out in the depth laminar structure of the cortex? So there are a few hypotheses that you might kind of put forward here. One is to say, okay, well, if my, say, ECOG contact they put in this XY coordinate is showing sensitivity to, let's say, plosive sounds, then maybe all of the neurons underneath that contact all are responding to plosive sounds. And maybe that's what gives rise to the response you see at the surface. Or perhaps actually different neurons are encoding different speech properties. And maybe there's kind of a dominance which explains what you can observe at the surface, but it's not to say that all of the neurons are going to have exactly the same tuning profile. So there are a few questions that we want to address here. So first, if we do have access to single neurons in this brain area, what do we find that those single neurons are actually encoding? And second, how is that tuning actually organized as a function of cortical depth? But before we get to those really interesting questions, we kind of need to address question 0, which is how we record single neurons across the depth in humans. And that's where these neuropixel probes come in. So this is a probe which was developed a few years ago, and this has been really transformative for animal model work because it gives you the ability to record from hundreds, and if you're lucky, thousands of neurons at the same time across the cortical depth. So you have, this is what you're recording from. You can barely see it on this projector because it's so thin. The probe is 1 centimeter long and extremely thin. And along that 1 centimeter, you can choose to record from 400 contacts. Yeah, I kind of like to perspective. Those contacts are actually smaller than the neurons themselves. So yeah, this is a really incredible kind of engineering feat. A lot of my postdoc was dedicated to trying to make it possible to record in the operating room with these neuropixels probes. So this would be the context where someone needs to have a brain surgery as either to treat epilepsy or to have a tumor resection. And we'll insert this probe into tissue which is about to be removed as part of their clinical treatment. But it's not pathological of itself. So the surgeon tends to remove slightly outside of the pathological tissue to make sure they're removing all of the pathological tissue. And we're kind of putting it in that kind of sweet spot in the middle. So there's all tissue to be removed, but not pathological.
But aren't those epilepsy, aren't those usually in the hippocampus or interrun protected epilepsies, or usually in these high activity regions?
Yeah, there's a lot of variability. There does tend to be a higher proportion of people, but there are some cases where either
Lucky to get a patient where you have this in the auditory area, right?
it's uncommon, but it happens.
There are a few surgical sites in the country that tend to see those.
Yeah,
This is in 2 months.
that's great.
Oh my God.
And do they charge for that? They charge a lot of money for that, right?
$2,500.
You mean the probes or the surgery?
The hospital or the auditory.
Oh, you mean for the experimental?
Experimentally, the cost.
No, so the surgeons are not to be co-ops.
I see that.
Once you want to be co-ops.
Correct.
And also they get money from NIH through the grant.
Oh, I see, okay.
So they'll be incentive, but many of them would rather make 10 times as much, not waste their time doing something.
There'll be that,
Right.
then you can get some and
Is
stuff.
that correct?
Yeah.
They're putting that you work closely with.
Wow, this is really.
Yeah, this is funded by grant money, not by the patient.
So one other reason why you get a lot of auditory researchers from is because they want to put electrode grids to know where the auditory areas are, to avoid them when they do see.
Yeah.
Because that's really big deal if you lose your ability to hear.
Yeah, thank you, House. That's an important point. So the data I'll show you are all from awake brain surgeries. Why would you have an awake brain surgery? Because they need to do language mapping and other types of mapping where they stimulate different parts of the brain and have the person say, name pictures back to them. And if they have any trouble in, say, picture naming, while this certain area of the brain is stimulated, then don't remove that because it's causally related to the successful process. So we, after the mapping's been done, the surgeon then knows what tissue should be removed, and it's at that point then we know where we can insert the probe also. Okay, so I'm showing data from 5 patients, and this is a schematic of the probe insertion into an MRI here. So the probe is actually longer than the thickness of the gray matter. So we insert the probe such that it has some contacts in air and some contacts in white matter, so that we know that we're really spanning all of the layers in between.
So at that level, what do you get out of the white matter?
Sometimes very sparse neurons sometimes,
I see.
but in most of the cases, it's very clear, even from the physiology, when you've crossed that boundary from gray to white.
You're using it primarily as a spatial localizer.
Yeah. So we know where the surface is because the impedance changes dramatically once you're in tissue. And we also know where the white matter is because of the change in the physiology. We also, because this tissue is resected anyway, we actually perform histology missile staining on that tissue as an extra way of seeing where the layer boundaries are.
How do you do that?
So the tissue is removed for the surgical procedure.
Oh, wow.
Yeah, and then the part of the tissue which is around the probe, we then have collaborators review all of that stuff. Yeah. Okay, so what were the patients doing? They were listening to sentences, not synthesized this time. These are ordinarily said sentences. And some of these sentences we repeated to the patient 10 times, so that we could get an estimate of the reliability of the spiking across repetition. So this sentence, it was nobody's fault. I'm showing you the phonetic transcription and the spectrogram. Let's highlight the nasals here. This will become important later. And here is some of the spiking data. So the x-axis is time, which matches that spectrogram. And then the y-axis is each of those 10 repetitions of that same sentence. So I'm going to play you now the sentence with the spikes overlaid on top for the remaining, I think, 4 or 5 repetitions of this.
It was nobody's fault. It was nobody's fault. It was nobody's fault. It was nobody's fault.
Okay, so you get that each spike you heard was a spike. Each of those red lines is a spike visually. And I think you can really appreciate just how consistent the timing of the firing is of this particular neuron every time the same sentence is played. So let's look at the responses of the same neuron, but for a different sentence now. And again, I've highlighted the nasal sounds. And let's do the same thing. Listen to the sentence with the spikes overlaid.
Junior, what on earth's the matter with you? Junior, what on earth's the matter with you? Junior, what on earth's the matter with you?
Okay. So it seems, at least upon kind of looking at these rasters, that this neuron seems to fire in response to the nasal sounds in these sentences. So it was pretty well aligned to the end of the previous sentence. Here it's responding to both ends and ends in this sentence. Clearly there's some variability. Some nasals seem to be better nasals than others. And I'm also not going to get into that in this talk, but this, at least kind of on first glance at the data, it seems that these neurons are responding to the phonetic of the input.
From the mother, the nasal is a ma.
Yeah, so there's a right an N, an N, and an M.
Yeah.
Yeah.
Yes.
Yeah, and so this matches what I was just talking about of the way that speech is represented being in terms of these phonetic features. So nasal is one of those manner features I was talking about, and not represented in terms of individual phonemes. And I'll show you the kind of explicit test for that here. So if I fit a temporal receptive field model using all of the phonemes you can identify in English and try to predict, will a neuron spike or not, based on what phoneme just happened at different points. This is the neuron we were just listening to. So you can see there's very strong weight on M and N as a kind of intuitive to you, and essentially no weights anywhere else. So this seems to be a nasal unit. And we found a bunch of neurons that encode different phonetic features. So we have some that respond to high vowels or to low vowels, to fricatives, which is a manner of articulation, nasal, another manner of articulation, proximate, which is a manner also.
What does the lag mean there?
Yeah, so this is, so the previous step was the coding, trying to predict what the feature was based on the brain activity. Here I'm doing the opposite. So with all of the phonemes, predict, will the neuron spike or not? So this is the spike moment, and this is the lag looking back in time. So when a vowel happens earlier in time, it predicts a spike at T0.
It's about 100 milliseconds, which is kind of
the
time to propagate through the early stages until we get here.
Right.
That is no, I'm just asking. This is,
Yeah. And this like this timing matches what I showed you in the previous in terms of the when you begin to be able to decode the sound at about 100 milliseconds. That timing matches here on the single neuron level. Okay, so this is evidence that essentially the previous body of work, mine included, which suggests that phonetic features of what the brain uses to process speech seems to hold true at the single neuron level, given that we don't find evidence for individual phoneme representations. And you can do a systematic like model comparison, comparing the two, and the phonetic features clearly went out.
So if you were to, first of all, does the cat have a similar area, or the animals that she has been using everything?
There,
Parents, and then if you record from parents, we can see this.
Hasn't someone done that? I think you get something similar actually.
So the parents know about phonetic
no,
feature.
Because of because it's so tied to the spectrogram
I
input.
see, I see.
Yeah. Yeah, we do see here, if you compare a model where you're just using the spectrogram versus using the features win out. But they're so correlated, it's a marginal gain. Yeah.
Definitely in songbirds.
Oh, the same.
Will these neurons every layer or?
Thank you for moving this on. Okay, so good question. And we can answer it by saying that we looked at not just the acoustic phonetics, but a bunch of other features as well. So now I'm fitting a TRF model with a whole host of different speech properties. And one of the things we want to answer is, do these different properties localize systematically to different depths? So this is data from just one subject. So this is one cortical column, putatively. We've got depth now on the y-axis. And I'm going to show you, well, I'll just show you. So each dot is a different neuron, and the size of that dot is how well the phonetic features do at explaining whether or not that neuron will fire. And we find in the same column, not just encoding of phonetics, but also encoding of the relative pitch of the speaker, so this prosodic property. And there's significant but numerically much smaller contribution of a few other features as well. But what is really interesting here is one, we kind of already answered the question. It's not the one column doesn't encode all the same things. Here we see both phonetics and pitch encoding in the same place. And you can kind of already appreciate it in one subject, but if I group all the subjects' data together, you can see that across subjects, the phonetic properties localize deeper than the pitch properties. So if we compare this to the layer boundaries that we get from the Nissl stains, this is about layer 4-5, and this is about layer 2-3. So there does seem to be certain features seem to localize to certain depths.
So
So you're gonna ask if, given the laminar relationship that you described,
Yeah.
that suggests like an IO relationship as well.
Yeah, so ideally you would see some kind of communication between these different like layers. And I don't actually see that too clearly. So do you mean that like, so the representation of a vowel would then feed to these neurons, which from the vowels can derive the pitch?
Yeah, or given kind of inputs and the outputs to
To the actual layers.
yeah, to temporal, because
Yeah, right.
you'd see a lot of external input.
Right.
For
Yeah. Thank you. Sorry, I misunderstood. So yeah, I mean, I interpret perhaps layer 4-5 is getting inputs from the thalamus, which those representations kind of match with something phonetic, which is more instantaneous and can already readily be derived from the spectral input. And if pitch is in layer 2-3, where there's more recurrent connections,
yes,
that would also make sense relative to pitch, which is a more longer time scale feature. Also, this is relative pitch, not absolute. So you've already normalized for the pitch range of that speaker. So it's kind of is like a higher order feature that maybe does need some recurrence to be derived.
and the morphology of the cells of the neurons in this layer, what does it vary? What kind of, do you have kind of a neural anatomy, anatomical data? So what kind of neurons you have?
Yeah, so the only way I'm really able to subdivide cell types is based on the waveforms of the actual spikes
I
themselves.
see.
And you do see a separation based on kind of clustering the actual waveforms. which maybe relate to fast spiking and regular spiking neurons.
I see.
But I didn't find anything to tie the cell type to what it's encoding. I should maybe also say that we're in an operating room, so we have about 10 minutes of data per subject, which is very little. So a lot of the, yeah, I think we're limited in that respect as well.
I was wondering, how do you measure tuning in this graph? And let's say that we are looking at a layer where you have a lot of lateral inhibition units or neurons that might be broadly tuned to, let's say, acoustic phonetics, because they are inhibiting everything that is not the one phoneme that you want to encode for that pyramidal neuron that connects to. Wouldn't that mean that we might miss, if we are looking only at the tuning, some of the functional properties of some of the layers?
Yeah, that's an interesting point. I mean, the way that I figure out what they're tuned to is very simple, just with a linear TRF model. So if I have all of these features, about 50 of them in total, and I group these features into feature families and then do model comparisons. So if I have all of these 50 features, I remove the acoustic phonetics and I see how much explained variance was lost by virtue of removing those features from the model. And then I see which feature family caused the most detriment to the explained variance. That's how I figure out what color to put here. In terms of, I mean, and given how simple that is, maybe I am like missing some like interaction between the neurons. I tend to find that there's not that much suppression. So if the let's say taking this using this spectrogram model, if the spectrogram looks like the opposite of what that neuron is tuned to, it doesn't get kind of suppressed to zero. It will still have its baseline firing rate. So it seems to be really just kind of an activation function as opposed to a suppression function, which maybe partly gets your question. Okay, so I'm already over time, but I'm very grateful for your questions. But I'll wrap up, and then people have questions during the break. Yeah, so what we find relative to what we didn't know before is that if you look at one of these cortical columns, the neurons are not all tuned to the same thing. There is heterogeneous tuning, but they're tuned to a bunch of different things. And that's not what you see in primate auditory, say A1, for example. There you find that the column is functionally defined by having all of the neurons being tuned to the same thing. We're not seeing that here in this human higher order auditory area. We also see that even though there's tuning of different things, they're not just like randomly scattered salt and pepper. They do seem to systematically localize to different depths and putatively to different layers with functional purposes of that. And right, I didn't say this, but how cool is it that in the same column you have encoding of instantaneous phonetics and this much longer timescale pitch feature as well? And to me, that's really amazing. Kind of speaks to the parallel aspect of processing. The brain has very local, extremely local access to these two very different timescales. And I think that tells us something important about how the brain is solving comprehension. Where should you have first?
Go ahead, sorry.
I don't know, I was there.
So in the picture you showed where we discussed or mentioned the delay one, you're not saying that there are different timescales that correspond to that kind of delay, different phonemes? For example, a phoneme that occurred 500.
Oh, I don't see that in the neuron, in a single neuron data.
So the multiple timescales here.
Yeah.
Simply refer to
the feature timescale.
Phoneme features, which are what you call instantaneous,
right?
Rather rapid would be at the bottom of your delay line.
I think we're talking about two, I'm not sure that the delay line,
You know, in the picture would be.
yeah.
You had phonemes emerging in the same slot and the same
Right,
whatever,
right,
cross section. And that implies that the top neurons in that slot have long time constants, have long time scales.
mhm,
They remember things
Yeah.
longer
yeah,
than the ones at the bottom.
right,
That's
Right.
not mirrored here, right?
yeah, here I essentially only see the neurons that would be at the lowest part of that
Yeah.
delay line. Which maybe because, I don't know, but I hypothesize as you go along the delay line, maybe it becomes more distributed, the code, and so on any individual neuron, the signal will be weaker.
So pitch is a totally different feature than the phonemes.
Yeah, right,
And so you're right, it hasn't. It may,
Could it be that
you know,
each,
I'm just saying, pitch is rather instantaneous actually.
yeah,
I
You
mean,
mean you
it's as
can-
fast as recognizing even a tone. Within 20-30 milliseconds, you can tell the pitch of a complex. Then, so maybe all the slab is different features, but the same time state.
yeah, I see what you're saying,
Or comparable.
yeah,
pitch is binding? Could it be that pitch is the binding signal?
yeah, it's possible, like, as you end the intonational phrase, that's a kind of indication that you should combine the stuff in the phrase before, yeah. I did break up the data actually into phrase boundaries and didn't see anything particularly, yeah, I did that. Yeah.
Do you think there might be some implications from the sparse sampling? Because when you're putting down the neuropixel, right,
Yeah, you
you
don't
have
know what
limited
to get.
time,
Right,
and maybe the phonetic features are kind of more salt and pepper, whereas the pitch feature has a more global representation. Just kind of curious on your intuition there.
yeah, so, I mean, you can answer that with the ECOG data to, which in some cases for the people who are having surgeries to treat epilepsy rather than the tumors, we actually do have the ECOG data in the
Same
epilepsy
subjects.
monitoring unit, yeah. And so, right, I didn't talk about this here, but I have a whole analysis comparing the ECOG contact signal to the units below it. And yeah, if you look at it's true, pitch is distributed more over space than the phonetics, which seem to be kind of randomly scattered around. So yeah, it's almost like this spatial code is also different between those two. Is that what you were asking?
Yeah, just kind of curious about your
Yeah.
thoughts, knowing that you've operated on these scales.
Yeah.
You see at all, or did you look for something longer than phone, like syllabic representations or such things? I mean, you have to do it literally the way you did for phonemes.
Yeah.
Right, I recognize it.
Right. Yeah, again, I'm just limited by the data. So as soon as you start to get to like bigrams, it explodes and you just don't have enough instances of each bigram to know. I did do a bit of more kind of like eye by eye, seeing if there were responses to more than one phoneme or phonetic feature with a systematic delay. I didn't find too many examples of that, so I don't think that there's representations here of something larger than. Okay, well, I guess I'll show you my summary slide. Well, yes. Go there. Okay, thanks so much.
I'm very mindful of the fact that many of you in the room are cruising towards amazing demos and research outcomes over the next couple of days, and I won't be offended if you think that you need to go get some stuff done. But I mean, always excited to talk about AI. I'm always excited to talk a little bit about some perspectives on where the field has come from and is going, and especially at this consequential moment for AI, everyone's kind of asking. And so I wanted to say thanks to Chia for making me give this talk. I guess a bunch of you remember a similar one in like 2018 or 2019, where I was like, there's this thing called the language model, and you're going to hear about it a lot in the coming years because it's changing the way that we do language processing. So now we're going to show you how we got from there to here, where we're headed next, maybe. And then also, some perspectives on where organizations like MITRE and the US government in supporting research in this area are looking, how we're looking to society as we move forward. So one of the things that I'm going to say, for folks who aren't speaking, AI language model native tokens, these are all things that make perfect sense to someone who's been paying attention for the last 6 months. Where are we going to be 6 months from now? We're going to try and map it out. By the way, this image over here, you've heard it over the course of this webinar, you heard me talk about diffusion models quite a bit, and this is an example of kind of like where we are with the state of the art with the ability to generate images. On one hand, it's remarkably impressive that you can say, show me a roadmap, signs, and make it an infographic style. And at the same time, it's impressive because it's made by a machine, but you're still getting, this is what it thinks words look like, and so it draws some words down there. And so I want you to keep in mind that at all times when you see the outputs of these machines, it's really impressive, but it's kind of like impressive. Is it impressive from the perspective of like, wow, you got a dog to talk? Or is it impressive from the perspective of like, this dog is going to teach us some physics? So it's, yeah.
I'm confused. What? I thought GPT-3 is just the older version of GPT-4, but you're putting them in different.
I am. We're about to talk about that.
Oh, you are? Okay.
Yep, exactly, yeah. So
I would like to know if the emails that I'm getting from Wednesday about my complaints about my condo are generated by ChatGPT, because they should sound like it.
Excellent. Okay, so the answer is probably everyone knew this stuff.
No, they don't back my complaints, they don't comment anything.
Oh, yeah, that's a perfect thing for an algorithm to do, right? That's a really good use case. So I'll talk a little bit about our work detecting GPT as well. I think it's interesting stuff. Okay, so first thing I always have to do when I tell people that I work for MITRE is explain what is MITRE. And so MITRE is this really weird class of organization. We're a nonprofit organization. We operate what are called federally funded research and development centers. And here you can see that we actually operate 6 different FFRDCs. Each one of these things is designed to be like a scientific expert that the government can call upon and ask us to help them solve problems and analyze the state of the art, make forecasts of where we're headed, understand how to integrate technology, understand how to evaluate technology, et cetera, et cetera. So one of the things that I find myself doing quite a bit is going and talking to government around, how should we incorporate neuromorphic engineering into our landscaping for the next 10 years? How should we understand the way that event-based sensing is going to transform different sensor missions, things like that? We're not going to talk a lot about that today. We're going to talk a little bit more about, our interest in AI specifically, but I'll just mention that we kind of work across every aspect of government, from the IRS to the FAA to the DoD to cybersecurity is an area where we can play very big role. Within the AI organization, within which I sit, we have a bunch of different thrusts, and I think this is kind of captures a little bit of how we look at the world. So you kind of got this notion of autonomous systems and things that have some agency out in the real world. You've got this notion of AI for perception, and this is a lot of common machine learning tasks. You've got things around language understanding and sense making, and kind of like making sense of the data in the world and assimilating it. And we've also got decision making, some ways that you kind of apply these things in a fashion that helps you do stuff that matters, and make humans into superhumans with AI. We partner quite a bit within the organization. That's a company of 10,000 people, right? So we have an awful lot of interests and applications that we consider, but we do a lot with modeling and simulation, human machine teaming, geospatial, healthcare, cyber, et cetera, et cetera. Okay, that's kind of like the obligatory what's MITRE, so now we can get into the interesting stuff. Within my research program, we have a really heavy focus on AI assurance. And this is one of the things everyone wonders about, is like, what's the impact on the world going to be? And we're wondering that too. And so we're hoping that we can help AI come up with for good. We're really interested in kind of this like strategic reasoning and course of action exploration. So, okay, that's the boilerplate. Now, we get into the fun stuff. I decided, let's make this a little man versus machine competition, right? Like I just told you what MITRE is, and presumably you got some understanding of what you think MITRE is from that. Now, an algorithm, Claude V2 was released yesterday by a company called Anthropic. So I logged into their new demo and said, explain MITRE using superhero analogies. And let's see if this is better or worse than my description. MITRE is like the Avengers, a powerhouse team of elite specialists. Government is like Nick Fury recruiting the best talent for important missions. I guess our engineers are like Iron Man, the masters of technology who build incredible futuristic tools. We've got Bruce Banner, who is, I guess, our scientists. Systems analysts or Black Widows see connections between and patterns no one else can. So oftentimes we're like helping government know about some other part of government that they should know about, but they don't. I really like this one. AI researchers are like vision, creating neural networks and machine learning to mimic human intelligence. Maybe. I guess that's me. So we come together to combine our superpowers to solve the biggest challenges facing government agencies today, just like the Avengers. Yeah, that's pretty much spot on. I think AI has clearly solved a lot of problems, and this is a good one. So now we get into the language stuff. I personally am a language scientist from way back, and one of the things you hear all the time is kind of like the explosion. ChatGPT comes out beginning of December 2022. Everyone said, like, who would have guessed it was going to be the language scientists who figured out how to cram all this intelligence into a computer? And I'm like, man, have you been paying any attention to the world for the last several millennia? Like the only way that humans encode information, create shared mental state between one another and pass it on through generations is through the creation of language and the creation of art, right? And so it's not unreasonable to imagine that if you have something that reads all of the things that are available to read, it's going to get really smart. And I got to say that you saw this if you came to the library talk, you saw a couple of these pieces. This is something that we've been working on computationally as a field, basically since the dawn of computers. So one of our first computational linguists, we might call him, J.R. Firth, back in 1957, came up with this famous phrase, which is, you don't know a word by the company it keeps. And that's just kind of really arguing for the role of context in the understanding of language. You know, if I ask you to fill in the blank in this sentence, your ability to perform that task depends on understanding the words around it. You can basically infer the meaning of whatever fits in that slot by the words that surround it. You know, if I tell you that a library is a word that is surrounded by a book and you know, verbs to tell you that you went somewhere, and you can infer the place full of books, and you can kind of start to understand like what are the affordances of it. And so really just at the statistical level, if you start counting what shows up next to other things, then you can really infer a lot about their meaning. And that's been driving a lot of computational linguistics this whole time. So back in 2015, I came to the workshop and we did a bunch of projects on word vec, this notion of embedding all words into a high dimensional space. And we got it working on an IBM you know, True North chip, and we showed that you could get like spiking neural networks to do all sorts of word understanding, word similarity, word sentence understanding, question understanding types of tasks, and that it's kind of a beautiful, it's ready-made analogies to biological computation, because realistically what I just described, this process of counting things and showing up, seeing how often they show up next to each other, is a coincidence detection task, right? You know, what are our synapses doing if not kind of like counting how often things show up near each other? And so you can kind of derive a lot of meaning just out of this co-occurrences calculations. And you see here that, you know, if you do that on Wikipedia, you get the library is like right next to archive and library and repository. And this is kind of old news, but like 10 years ago, people kind of jumped out of their shoes saying like, whoa, I think we're going to make some huge progress in language processing soon because of it. Language models like ChatGPT or GPT 1, 2, 3, 4 are really rooted in glorified autocomplete. And it's kind of, you know, a rude way to phrase it, but it is true. That a lot of our algorithms over the last 20 years have been focused on next word prediction. Again, one, because it's a good way to understand the sentence up until now, because if you can predict the next word, then you can have some confidence that you know what the sentence is saying. But it's also a useful task for some people. And so your phone and Google search have been kind of like trying to figure out how to take the way that you type things and say like, okay, well, I see what you said, but I know what you mean. And now I'm going to respond to that. And that's really kind of been the root of autocomplete, is like trying to say, what's the next thing that you meant to put here? And how do I like fix up your error-ridden typing in a way that is informed by the context? And so what's crazy is that you work on this stuff for decades. You use it to maybe correct some speech recognition output. You use it to correct some machine translation output. But now it is core AI, and everyone is kind of like, whoa, how did we get here? So now we're going to get into the details of why I listed all these things out in a bunch of discrete eras of large language models. So we're going to use this analogy. We're going to ask the machine successive eras of language models to complete this task of like telling us a story that combines Cinderella and running marathon. Yeah, you should like this one. The thing that I would point out is that up until 2019, 2020, even at the point in time when GPT-2 was the one that was deemed too dangerous to release by OpenAI, we were saying like if we put this onto the internet, society will be forever altered. Toby will get emails recapitulating his complaints, things like that. So even these early models were kind of deemed, quote unquote, confusable with intelligence, I guess what I would say. And you're going to see that we were pretty misguided then, and maybe we're pretty misguided now. So what this is doing is autoregressive text completion, right? It's just saying, given the words that have happened so far, let me continue that thought. And with GPT-2 or GPT-3 even, you get pretty pointless outputs if you just ask it to do something like this. It's read all the internet. It's noticed that the internet is full of sales copy, and it makes you a continuation of this thought that says, oh, you're writing a book about Cinderella and marathons. Here's how you get it published. Here's like, we have a special package for you. If you buy this, we'll help you get it out into the world. And so that's not useful. That's not useful to anyone. No one needs that. There's plenty of people babbling on the internet already. We don't need it. Something just babbling some more. So a lot of us were thinking like, wow, these claims of intelligence feel pretty overblown. It's just like a continuation of this statistical pattern completion thing. Where it gets really interesting for a little while was people started saying, okay, what if I get creative about how I ask it to continue? What if I imagine the task that I want it to do and then kind of like give it some prompt that lets it, complete the thing that I intended? And here you would start it with like, once upon a time, there was a girl named Cinderella and she loved to run and she always dreamed of running a marathon, and then you can get a story. But you're not going to get a particularly amazing story in this instance. In this case, I find it really concerning that it's a story about Cinderella and her husband and her son ran a marathon, and then she was running alongside a guy who would then become her husband. So I guess we're like home wrecking Cinderella in the story. So it's just kind of, again, it's just like a synthesis of the internet. Your ability to get anything useful out of it depends on your ability to get like a creative input prompts. But it's really trial and error. So at this point in time, we're still thinking like, neat tool, but is this going to change the world? Maybe, maybe not. Where
far back do they go regressively, so to speak, in order to predict the son and the husband and I don't know what?
So that's a good question. For any language model, you're mostly using a transformer-based architecture. You're asking about what's the context window.
Yeah.
Some of them might be 4,000 tokens. One thing that
4,000?
the big ones, yeah. So a smaller
words in the past.
So, which sounds like a lot. It sounds like a lot, but it isn't that much.
Tokens.
So, exactly, yeah. So tokens. So that's another. This is actually related to the question that you were asking in the break.
Yes.
It used to be that we had to worry about words that weren't in our vocabulary, and this was like one of the, what tokenization scheme do you use, et cetera, was really important. We have transitioned to a data-driven process where we break words apart into tokens that basically give you more or less complete coverage of the entire, infinite universe of things that could be said. So if this word alongside doesn't happen to be in your vocabulary because it's not in the top, let's say 50,000 words, then you would break it apart and say, okay, well, I recognize this along that makes sense to me, and side, and you just would put a marker on it that says they're attached to each other. And then you let the magic of the transformer architecture figure out that in context, along and side means something different than along by itself or side by itself. And so like everything in language is context driven, and that includes down to the sub word level. It includes up at the highest levels of this thing too. Like the meaning of a sentence is entirely dependent on the context in which it occurs as well.
This might be too early to ask, but I'm always baffled as to how these stories, for example, begin to build logic, sort of like an introduction and then something, and then they end up with a conclusion and a profound statement. How do they know?
We're going to talk about that a little bit.
Oh, okay.
Yeah. So, but Andreas actually could give you. He sent me a really cool paper on this that is in the works right now. So we can talk more about that too. Humans create stories with structure. So if you're learning from humans, you're going to be able to learn some structure. Exactly. But right here, I wouldn't say that it was particularly structure filled, right? Like this is just kind of like next word, next word, next word, stop, done. And we'll see better examples, and you can train that intentionally. So this is the moment, I think. The instruction tuning moment is the moment where we started to look at these things and say, whoa, they can do something useful. And I didn't see that coming. So it's a really simple concept. It's basically saying, instead of giving you a prompt and you read the prompt and give me the next word, it's saying you read the prompt and give me the next word in context of what your attempt to analyze the thing I'm asking you for is. And so you can train this behavior really simply. You can imagine, right? Like if we've been working in machine learning now for decades, we've created all these training and testings for the process, for example. So we might have like a Jeopardy data set. You take every Jeopardy question that's ever been made, you write it down and you say, okay, here's the question, here's the answer. Pass. What we're doing here is we're asking GPT-3 to figure out how to respond to something of the form, answer this Jeopardy question in the form of a question. And then you give it the question, but the answer, because it's Jeopardy, so this is a bad analogy, I guess. And then it is supposed to autocomplete, and it's not supposed to just give you random next words as if you're Alex Trebek asking this question. It's supposed to interpret that you're asking it for a Jeopardy thing, and then it'll go back and say, okay, well, let me do that specific task. And so you're really giving task-specific instructions on thousands of different tasks. You would say, please answer the following question, what's the boiling point of nitrogen? Whereas in the past, we would have said, what's the boiling point of nitrogen? And it would autocomplete with some boring thing about nitrogen. Here, it recognizes it just wants to be, it's being asked for a concise answer of a number. And maybe it can produce that. The thing that's really fascinating about this is that you kind of get this for free because you can exploit the labor of every grad student ever before whoever had to create some data set to evaluate their previous algorithms. And so now you're asking one language model to learn how to do all of the tasks that we've ever asked a single algorithm to do. And it turns out there's some ability for an algorithm, 175 billion parameters in it, to learn how to kind of like synthesize these instructions in ways that are potentially generalizable. But it really has its roots in teaching the algorithm that what you're doing is giving it code, not something to be completed. It's really, you're saying, program me with this prompt instead of give me an autocomplete prompt. So let's go back to the marathon example. In this case, you can think of every Aesop's fable that was ever written as a training example. You would say, take the story, maybe extract the title, and then you turn it into a prompt that says, write me an Aesop's fable with the title, The Fox and the Grapes, right? Or whatever. And then the quote unquote right answer, so again, this is in a supervised fashion, is going to be the actual story that you found out in the world. And so this is how you basically get all these copyright violations getting crammed into a GPT, right? You're showing it all this cool stuff. You're showing it textbooks, you're showing it Wikipedia, you're showing it everything that anyone has ever written down and put on the internet, and you're turning it into a question, using some kind of like hacky thing. and then saying, okay, you get this question, just the right answer.
So why do you have all these boxes up here?
These are examples of types of tasks that people have used. So there's actually, there is a data set that has been aggregated as a synthesis of many, many, many other data sets. And it's kind of like your standard. If you wanted to take your language model and train it on instructions, here's a data set of 2,000 kinds of tasks that have instructions.
How do you identify instruction and corresponding answers from random data on the internet? Like if I go to a forum, how do they, the engineering of the data set, like how do they?
So this is a really creative process, right? So if I'm going on a forum, you might take the first post, and then you would take the replies to it, and you might make a task that says, write a reply to this first post. And then if you wanted it to be controllable, you might run like an algorithm that does sentiment analysis, and you find one that's really angry, and then you could say, okay, write an angry reply to this post. And then you might find one that is like in strong agreement, and you would say, write a post that is in strong agreement with this.
So it's a very manual work, like it needs a lot of.
Sort of, but what I just described is using the tools of previous language processing eras to create these prompts for you, right? So you can take your favorite sentiment analysis program, you can run it on all of the Reddit posts and get together a data set of the most extreme in every direction with very low cost, you know? And that's, yeah.
But each one of these models will have an associated error, right?
Yep.
So some of that will creep in the training set.
And there's no right answer to any of these questions either, right? Like just because I say write me an angry reply to Toby's, you know, whatever, doesn't mean that there's only one thing that you could do. But that's 175 billion parameters. You're generalizing pretty broadly across lots of glimpses of different data that is absolutely error prone. You might ask yourself, what does this mean, you know, for the rigorousness and the truthfulness of any algorithm that's trained on internet scale data, which is full of lies and inaccuracies, in addition to the ones that it introduces through bad programming. And you would be right to ask that question, right? So this is why we should consider the origins of these things and the way that they were trained when we're considering how to use them. So yeah.
I still understand, Guido, this 2SF, what is that?
Okay.
Things?
Yeah, so these are class of tasks. Basically, these are types of algorithms that people might have used before. So, you know, question answering is like a pretty common data set task that you might find. You know, here's a passage, answer a question about it. Common sense reasoning. Another thing is like your SAT questions, you know.
Why is in this 2SF? What does 2SF mean even?
This is coming out of, it's basically just like an aggregation of 55 data sets here, 9 data sets here. It's basically a observation that this is happening in many different places in the field. There is someone who made a 2SF, I don't even know what it stands for. Someone made that data set benchmark. Someone who made a natural instructions version 1 and version 2. And then someone who said, you're all duplicating efforts, let's pull this together into one super mega data set. And so at this point, you would now, as your first stop, if you're training an LLM to follow instructions, the first thing you would do is you go grab this super mega data set and train your algorithm on all 2,000 or beyond tasks. And that way we learn a little bit about how to generalize between different types of tasks that it's asked to do.
This is if you were to start from scratch.
Yes. And this is, so basically what we're describing here is the step between GPT-3 and what was called GPT 3.5. And the interesting thing about this is that this instruction following version of GPT-3 was on the OpenAI website for about a year before ChatGPT came out. And when ChatGPT became super famous, everyone at OpenAI was really confused because they're like, we had this on our website forever, and we don't think that ChatGPT is a huge advance.
Or like super pissed off.
Yeah, they were like, I mean, they were really excited because they just caught lightning in a bottle, but they were also like, we already told the world that we were doing this. And, you know, like we just read a paper about it, made our own version of things and made an API for it. And so you can find it on their API hub today. It's basically 3.5 is what they were calling it. Now, the interesting thing is that it doesn't solve all of our problems by itself. So there are advances that made ChatGPT better than GPT 3.5, and I'll show you that in a second. But I'll show you some examples of what happens if you ask it for a marathon story here. So, and by the way, the first one is something that we're running locally at MITRE on our AI hardware. This is ChatGPT, or sorry, GPT 3.5. First one is, let's see, Cinderella is an ordinary girl who wanted to be extraordinary. Kind of goes into like she wants to be fit and healthy, and so she works really hard. And she puts in the effort and she runs a marathon, and it's basically like, good for her. We should all work hard to achieve our goals and live our dreams, just like Cinderella can be extraordinary. Same thing with GPT 3.5. You would read the story, you would say like, okay, you have a story that contains the name Cinderella and running marathons. And in fact, it actually, kind of to your point, it includes like a little moral at the end. But it's not really like, if I told you to write a story about Cinderella running marathons, you would think like the Cinderella story is like glass slippers and clock striking midnight and stuff, and you're thinking like, that's missing, you know? So we didn't ask for that. It followed our instructions, but it followed our instructions in something sort of mechanical. Very impressive, don't get me wrong, but kind of mechanical. It's not a good story. So the question is, how do you get a good story out of the infinite number of stories that you could ask it to write? Well, the answer is you train it on that task. And OpenAI and everyone else is spending millions of dollars asking people to do this next step, which is, yeah.
So your story on top was better than the story that you get out of ChatGPT.
Yeah, let's see. So
I don't know if people had the time to read.
Yeah, so the bottom one is once upon a time, Cinderella, a woman named Cinderella had a passion for running. She would go run around the kingdom. And it's this very similar type of thing where it's kind of like this inspirational, like she had to work really hard for it and she did it. By golly, isn't that cool? And you know, whether or not you get a better one out of the top or the bottom, don't read too much into that, because we could hit the generate button 100 times to get 100 different versions of these things. The way that we phrase it is going to alter the output. So, I mean, I think it's worth noting that you can get really good performance on tasks that you might be interested in out of models that are not at the scale of you need a city's electric grid powering them. You know, not that 11 billion parameters is a small model, but it's not 175
By the
billion.
way, can I ask a rather naive question?
Yeah, of
Where
course.
does the noise come from? Where does the randomness come from?
So at every step, this is still autoregressive. So in fact, you'll see over here that there's like some sampling parameters. Yep. So you're sampling from a distribution, probability distribution of the next word. And so this is still autocomplete, and it's still saying like, I think after once upon a, 99.8% of the time, the next word is going to be time. And so you're going to have a hard time sampling your way down a different path than that. But there's a lot of places where, you might make a choice here that dramatically affects the, the choice down here. And so it kind of cascades as you go. And it's actually worth noting that if you ask one of these models like a riddle, and it answers the riddle and then tries to explain its reasoning, you'll find this situation where it'll give you a wrong answer. And then it will have to contort itself into a pretzel in order to try and come up with an explanation for why that's correct. And that's because it needs to stay, like it is already sampled the fact that the Cinderella in this story is a woman. So everything that comes after it needs to be consistent with that. You can't start mixing pronouns later on. And so the transformer architecture is really good at doing that, but it will get you into some real trouble if you make a mistake early on and then suddenly you have to say like, well, because the universe is smaller than the moon, then it has to like try and come up with some way to be consistent with whatever it is set up front. So
And politicians are like that too.
yeah, exactly. In addition, they're similar to GPT in that it's also trying to tell you what you want to hear. So it's just like predicting something that is likely to not get it penalized, which is fits the distribution. Doesn't need to be correct, it just needs to fit the distribution.
You didn't say anything about that particular point. How does it react to quote unquote us?
That's next slide.
But it could be an issue of prompt, right? When you put prompt it to say like, okay, give me more of a story which is associated with fairy tale. And then because I can see the GPT may have recognized and realized any bird. And then it seems that marathon and all that inspiration is what you find on the web more often.
Yeah. Right? Yeah, I mean, so there's magic in all of the prompting for sure. But one of the points that I want to make is that a non-trivial amount of the magic of how you make these things useful is in this next step of alignment to human values, which I think is a really inspirational story for people working in AI, because like everyone kind of talks about like AI safety as this separate thing. Like we're going to make the AI and then we're going to worry about if we can make it safe or useful later on. The thing that I like to point out is that the process of making GPT 3.5 quote unquote safer or more aligned human values is precisely the thing that made it interesting to everyone and therefore caused it to become useful and productive. And so like this is kind of a cool story of like AI alignment is the reason why OpenAI is making billions and billions of dollars in market cap off of their release of this API, is because they were the first to kind of demonstrate a tech that you could combine some techniques that included alignment in a way that made it suddenly interesting to everyone. So remember that message. But the thing that we're talking about here is like, we just wrote a bunch of stories. They are technically correct. They are stories about them running marathons. The algorithm should have gotten, not huge gradients for that, right? Like that was a pretty good generation of a grammatically and semantically correct story. It's just not a fun story. And when people say, tell me a story, they want to be entertained. They're asking for you to entertain them. So the way that you encode that into the machine is you ask it to sample 1 million stories or 3. You ask it to sample a bunch of stories and then you show it to some crowdsourced person on the internet and say, which one's better? What do you like better? And you can use the relative rankings of the outputs to say, okay, we're going to guide the sampling strategy. So this isn't even, really retraining the whole network. This is just, again, built on top of the previous network. But we're going to prefer a sampling strategy that has a reward that is driven by reward in terms of which people like better. And there's a lot of ways you can decide how much you like a thing. So I'll give you an example. Claude, which is what wrote my superhero introduction, uses something called constitutional AI, which is basically a way of saying like, you will be a fair, unbiased, basically it uses the, literally uses like the Declaration of Human Rights and a handful of other well understood philosophical stances on how to treat people. And it says, your output must conform to this. And they make classifiers that say, is this something that embodies this principle? And then they use that classifier to consider versions of different outputs and say, okay, this one is more fair according to the definition of fairness that we learned, or this one is more committed to democratic ideals, or this one is more, whatever, yeah.
Yeah, no, I'm curious, because you're saying basically the strategy is to have people rating what they find more entertaining and then feeding back to the system. So once I asked you to write me a story that I was hoping that at the end it would be full of, what's the word, stereotypes. Basically, I asked you to write a story about, something involved in technology, so I expected to be a man, so on and so forth.
Yeah.
And actually, the story that you wrote to me was going the opposite way against all stereotypes. So is that trained? Was there a group of people saying, no, this is
yes, absolutely yes. Yeah, because you have to imagine that GPT-3 alone is just a typical machine. So it's going to replicate every behavior it finds in its training data, which in proportion to the extent that it was observed, roughly, and that is dangerous. And so one of the ways that you guide these models away from that behavior is explicitly what I'm describing right now, this process of saying, you wrote me 2 stories, maybe I have a classifier that says this one is full of harmful stereotypes, this one is not, I prefer this one. And so then you have a reinforcement learning algorithm, which is going back and altering basically the final, your sampling strategy and kind of like the distributions of tokens at that point. It's still informed by all the 175 billion parameters sitting underneath it. But now when it gets to make a choice that it's going to say he or she, that it can make the choice that better conform to the societal ideals, rather than statistical biases. And it's not going to solve all of our problems because some of these things are in tension with one another, which is really important, right? Like so Google trained theirs. If you remember the dude, we actually talked about him at last year's workshop. A guy had gotten fired because he thought that Google's chatbot was sentient, right? And then, again, remember, this is for ChatGPT. So when ChatGPT comes out and OpenAI is like, why are you all so blown away? And Google's like, didn't we tell you about the dude that we fired because he was like best friends with our robot? It really has been a long time coming. This is not like some discrete moment. But theirs was trained on these, their chatbot was trained on these different values, right? So sensibleness, so it's got to be, you know, I got to be able to understand its output. Specific, so it has to be taking a stance. It can't just say like, oh, I don't know, because that's a really easy answer, and they will learn, an algorithm will learn to say, I don't know to a lot of things, because it almost never gets penalized for that, unless you make an I don't know detector and say, I want a specific answer. It has to be interesting, because, you know, what's the point of having a chatbot if it's just going to be like, I'm fine, thanks. Right, like, so, you know, so okay, go on. So it has to be safe, which would include some of these notions of like, what are the behaviors that we find harmful and how do we get them out? Groundedness, so it needs to actually be willing to refer to things that are quote unquote facts. It will be rewarded for, you know, being grounded in real stuff rather than just hypothesizing. Helpful in that you don't want to make a robot that is just like has its own ends. You know, it's supposed to be a chatbot that is useful, and so that means it needs to have like a helpful mentality. And then role consistency, which is that people find it really jarring if it's, you know, you start out chatting with a bot that says I am an AI language model, and then later on it's like I'm a famous scientist and I am, you know, so it has to be consistent across time. And so that's what it takes to make a robot that someone is going to say is sentient can get fired for. But everyone has their own different take on what you're training into these things. And ChatGPT was that version of GPT 3.5 that used OpenAI's proprietary alignments.
But how did they label that? They took humans to label,
Yes.
like with sliders?
Yep.
You know, all these things for
Exactly.
everything.
You got it.
OpenAI hired 30 experts in 30 different areas at a cost of about $2 million for 2 years. So they gave them $1 million a year.
Yep.
To really do this, which is nothing.
Yep.
I mean, just to read these
Yes,
stories.
Exactly. Yeah.
Yeah.
And maybe not great examples, but mostly to read and rank.
It tells you all the topics and the people.
And so one of the things that I'll point out is that ChatGPT and a handful of others since are really good at writing code. And that's not accidental, you know, so part of it is the first thing that they did was train it on all of GitHub. And it's kind of interesting that you can get emulation of a logical reasoning out of reading code, right? Like there's some generalization power in reading code in the same model that's reading language, because you kind of learn that things affect other things, and you kind of learn that you need to build up states that can be modified in ways that are programmatic. But they really have invested probably tens of millions of dollars at this point, hiring programmers to do tasks to explain their reasoning as they go, to say like, well, the first line is going to take this variable and manipulate it in this way. And so they document it, they type it. Now you can then do something like run the code, and you can use this reinforcement learning from human feedback. It doesn't need to be human. You could say, okay, that didn't compile. That didn't have the expected output. And that's the type of feedback. And so again, you're guiding your sampling towards valid source code syntax. You're guiding your output towards things that do more correct, better naming of variables and more consistent use of the same variables rather than functions, et cetera. So all these same things that work on language work on code. And this is where you insert it. So it's not you train it from the beginning just to do code. You take something that does all the stuff we talked about, and then you start showing you examples of coders doing code, and then say like, this is a better one than that one. And it'll eventually learn to bias its output sampling strategy towards things that are more valid and more useful. And I hope everyone at this workshop is using code tools like this, because it is a superpower. Honestly, it is actually really impressive how useful these things can be for some of the the stupid things that would take us, you know, just 20 minutes to write from scratch. Now it's 2 seconds to write from scratch, and So then you're trying to solve the problem.
But if you can write code, I mean, you can ask to write.
Yeah.
Code for anything you want.
Yes, and it won't.
Or C++, so.
Yeah.
You know,
All right, so we'll show you what happens with Cinderella, and then we'll get into some of the other implications. So I gotta say, this was my first try. This isn't cherry picked. I thought this was freaking great, right? So it's like, once upon a time, there's a girl named Cindy who loved to run marathons, training for months. Yeah, right. Training for months to run in the Royal Marathon, but her wicked stepmother. Finally, we get the wicked stepmother in the story, right? And stepsisters didn't want her to participate, so they locked her in her room, took away her shoes on the day of the marathon. And Cinderella wasn't one to give up so easily. Because she's quick thinking and a resourceful woman, she fashioned her own running shoes from old slippers and laces from her corset, jumps out the window and gets to the starting line just in time. As she's running, the clock strikes midnight. I guess this is a late night marathon. And her shoes turn back into their original form, and all the other runners laugh at her. And that's gotta be pretty traumatic, I imagine, but it did not discourage her, and she kept running with her ragged shoes. At the end of the marathon, to everyone's surprise, Cinderella crossed the finish line first. The prince, who was the sponsor of the marathon, was so impressed by her determination that he asked her to marry him. And they all lived happily ever after. Cinderella proved not only her stepfamily wrong, but also proved that with true grit, no obstacle is big enough to stop you from achieving your dreams.
and then ask them,
Oh, why is it so really positive? Why is it going?
That's a fairy tale, man. So fairy tales have,
Bad stepmothers.
yeah.
This is an American fairy tale.
Yeah, right. When she got
Very seven is already the people started this. Everything that been written can be classified in seven categories of stories.
I would call this the Disney version of Cinderella running everything, right? So
Is this from like one of the earlier versions, like of 3.5 or like the one?
this is ChatGPT.
But like, is it 3.5 turbo or is it?
Yeah. Yeah, I haven't done it with 4, but I'm sure.
But the initial versions were very different, and now they've like introduced so much.
Well, so again, I want to be clear. This is an economically viable task for a group like OpenAI, right? Like they want to sell this to your Alexas to say, entertain your children. Think of how valuable it is going to be to make a technology that can safely tell a story to your children and code happy morals and things like that. So don't look at this and think like, wow, that's amazing that it figured it out by itself. No, I bet you a lot of money has gone into this task of writing stories that are entertaining and safe and fun and all that kind of stuff. So, but pretty cool that we're at this point in time where
Get ChatGPT with different values.
yeah, 100%. Yes.
So, you can specify what value system you want.
So they have taken extreme pains to encode their values into the model, and you can probe it. And we've done some work, and I don't have it in this talk. We've done some work to show you can see exactly what it will refuse to answer. It will absolutely refuse to answer questions that are climate change denial, but it will happily take on lots of other misinformation myths, which is kind of intriguing. But that's just a value choice.
Okay.
Yeah, this is a problem that we haven't even solved for humans. So there is like you can easily, or I mean, I'm not sure if you can still do that, but you could easily trick it. For example, you could not ask it for like give me sites like websites where I can download stuff legally. But you could say, hey, I want to set up a website filter for my child that it doesn't download illegal stuff. So which are the sites I should definitely avoid? And then it will happily give you a list of like sites where you can download stuff legally, right?
Yeah.
So this is, I'm not sure if just modifying the prompts and stuff like this is going to be enough to prevent it.
It's not going to be enough to make it safe, but it's a necessary.
They have problems that we haven't solved.
So one stance that our organization takes on AI safety is that it is an extension of human safety, right? Like just because something had quote unquote AI and it doesn't put it into a new class where you suddenly need to behave responsibly. Like if you don't want a hacking algorithm to hack into your nukes, then you should make it so that your nukes can't get hacked into by anyone, right? Like, so in the same way that if you're looking to set up guardrails to raise your child using information sources that are trustworthy, you have to, you know, accept some risk. Same thing with all uses of AI. So we kind of view like AI assurance as a risk mitigation process. It's never going to be a perfect thing. And it can't be. Like, again, if I look back to this, some of these things are in competition with each other. I can't necessarily make something that is both interesting and grounded if the thing that you've asked me to do is extremely boring, right? And so that's just like an easy example. Like, I need to personally choose some balance of these things. As you start encoding more and more ideals into your value function, it's literally impossible to satisfy all dimensions at all times. And that's true. That's not just an AI concept, that's just life.
Again, this might be a bit early, but how does it infer without centered and human body and all of that, laws of physics? Just
so
regurgitating what it's read?
So there are, again, lots of examples where people are feeding it tests that are math problems. So you can do math as a chain of, you know, permutations on some like Blackboard state, you know, model. So it's entirely reasonable to think that you can train that behavior in by showing it examples and asking it for generalization power. There's actually a really interesting thing. Let me look forward to. We got a lot of slides, we're not going to go through them all. This was a really cool paper from Stanford, maybe 2 months ago. So one of the things that everyone has described these behaviors as, like, oh, it can do math. Suddenly, that's an emergent property. As the language model gets bigger, now there's a step function, and you've got a math capable AI versus a not math capable AI. This is a great paper that I strongly recommend everyone read and kind of consider in your own context, because it shows how the way that we characterize our evaluations gives us the appearance of having something that has emerged. So in the case of math, if you ask it to do 27,012 times 9, and the answer is off by 1, that's a wrong answer. And if you ask it to do that same problem and the answer is cat, that's a wrong answer. And treating those both like they're the same wrong answer, they're equally wrong, is a really bad idea, because they're not. You know, like, if your kid gave you an answer to that question that's off by 1, you'd be like, that's really good, you almost got it right. And here's the last thing that you need to understand. But all of our metrics are pretty binary. And so it turns out that a lot of models between here and a math capable ChatGPT were kind of close. And it only made it look like a step function because we gave them 0 credit for partial answers. And we did that in a lot of different benchmarks. You know, question answering and reasoning are really hard things to evaluate. And so if you choose the wrong evaluation function, it makes it look like it showed up out of nowhere. But for the most part.
But do you think that text and all of these sources now will be sufficient to replace the experience of actually having body, or?
No, but I do think that there are, so, you know, the groundedness question is something that.
Yeah, that's why I remember the grounding, the common sense.
Yeah, so I would say no, it's not sufficient. It's not a, you know, you can't replace it entirely. But for many of the types of outcomes you might desire, it's possible to encode those things into descriptions of experiences that you can train it on. So I don't think it's a binary thing. I think it is possible that I believe that we will get to a point in time where machines that are trained in a grounded way will be much more capable of interacting with the world around them. One thing that is a huge challenge for all of us is that the amount of experience you can get with the world is dwarfed in comparison by the amount of text on the internet, right? So you can train 175 billion parameter neural network on every word ever written, and you know some significant fraction of that. But I remember actually a couple of years ago, OpenAI got out of like the robotics game, like manipulation and hand grasping and whatnot. And they were talking about how they were having a hard time giving enough, like a rich enough set of experiences to the machines such that it could generalize. And you're like, it's amazing. They just said that like the real world, actual physics is not a rich enough experience to train a machine. But the problem is that it's too slow. You know, you got to do it in as parts burn out. You can't get 20 trillion examples of trying to grasp so while we're in this era of like, we're great at computing, we're great at cramming information into massive networks of connections, we're still really far away from data and label efficient learning. And that is why the groundedness problem is hard to crack. However, starting with something like this, and then building off of that and putting it in a situation where I can experience simulation or experience the world. Awesome. So yeah.
Guido, can you comment on what in my mind is really mind-blowing? The fact that we can go from pixels to words in these models.
Yeah.
So I don't know if people know that you take a picture of your refrigerator and you ask it, what can I cook with words here? And from the pixels, it will give you basically some kind of a recipe. Of what,
conceptual.
because they don't do image recognition explicitly.
They have to. I mean,
No, they
otherwise,
don't.
how do they know?
They
Yeah, so the GPT-4 models have been trained on multimodal input, which means they do have image encoders as vision, you know, doing vision, as well as language encoders doing all this. The way that we train up those models is you are again doing it in just kind of like this massive data dump fashion, where you have like Stable Diffusion, for example, is trained on 6 billion image caption pairs. And so you can do a task where you show it a picture and it runs it through convolutional neural network or whatever, probably a vision transformer. And then you show it something like 30,000 potential captions. It has to read each caption and say, this is the one that is the best fit for this picture. And you train that using all the electricity in the world, all, you know, grab your favorite TPU pod and run this task for as long as you can bear it. And at the end, you get something that has a really good ability to map image descriptions and images into the same common space. So once again, it's a huge data-driven undertaking. And there's clever ways to ask models to do all these things such that you can take advantage of the computational firepower that exists today. But that doesn't answer the question of like, what is not learnable without a physical body, or, you know, what, like, it can tell stories that contain emotions in them that give it the appearance that it has some understanding of what it is talking about, but it is, again, a statistical process. So, you know, like, you can learn that these patterns evoke this type of emotional response, and that I get rewarded for this kind of emotional response by the reinforcement learning. So it's a statistical process all the way down.
So is that all there is to us?
Yeah, maybe, right? Right?
That's
the question.
People worry about.
Existential crisis.
Yeah, the question isn't, is AI intelligent? It's people.
Disagree
With which?
with this notion that this is all there is to us, like what is there out there that is not?
No, so I would also argue that like there's all sorts of really cool things going on in our brains that
Like what?
like the fact that neuromodulation, I think, is a really cool concept that is not represented in ChatGPT, right? Like, we should look into that. I think that would be a really cool contribution of our field, to understand how you modulate a network's behaviors according not to by training it, by understanding how you train it in ways that you can then provide some chemical context later on that changes behavior.
I just wanted to add to that page and say that in order to learn how to speak, I definitely didn't scan the entire internet when I was a kid. So there must be some priority than maybe are.
Oh, you're playing right into the Chomsky debate that we had last year, so this is gonna probably. So Shiab and I are going on a trail run tomorrow, and I expect that's gonna be one of the topics. We're gonna table that until tomorrow.
What is your opinion in terms of number of parameters these models have comparing to the biological, like the rat, or it's not that much larger than the rat?
Yeah, it's totally inappropriate to compare parameters in a floating, like flops to biological computation. Like how many flops are in a single neuron is not an answer that you can't give me an answer to that question right now. Like is how much of the dendritic tree is performing computation versus like signal relay? How much like it's wrong to look at the number of neurons and the number of synapses that we've got and to map directly over into the deep neural network and draw that comparison. So I think the human brain is vastly more powerful. Now not as good at memorization, but that's by evolutionary design. If you remembered every detail of everything that ever happened, you'd have a really hard time generalizing into the future. So we got to compress things to make it fun.
But if following that, if you think that our brain is much more powerful, right? Then it's like still you can make a conclusion that this is somewhat like the rat's brain is comparative to that, right? I mean, it's vastly more powerful. So it just kind of, you can look at that we can compress all the information that we have.
Yeah.
Something that is comparable to that. Rat, if it will be concentrated on just learning the internet.
Yeah, I just don't think that there is a good analogy to be made between the two things. Like they're performing completely different objectives. Yeah.
I mean, just 2 comments. I think this is a very anthropomorphic comment. I mean, the rat is a very powerful machine. I don't know how much less powerful is in my brain. Second, for doing the task is doing, I cannot do the things that the rat is doing. Right? Are you kidding me? Second, when you talk about plots and mix and whatever, everybody forgets that the most parallel operation that is ignored is addressed decoding in the ESRAM to find the data that you want to process and bring it. That's it, log-n complexity, and that's massive. Every time you access a point, you don't run a Turing machine going and searching a tape linearly. You do it in parallel. And so maybe we should be thinking about more memory primitives as a comparison for the brain, Anyway.
Yeah.
I wanted to add on to Shiab's philosophical points. So for me, I think this is a new version of the question that people in philosophy of science have had for a very long time with like determinism and stuff like this, where basically like my analogy would be people in physics were saying if you know the position of every particle, you can basically simulate the entire universe forever. Position information, right? And the same thing in probability theory, if you have a joint distribution of everything, then you can also say everything about everything, right? And this is now the predictive version of that. If you have a predictive model that can predict everything from the previous works, whatever, in principle, you can do everything with it. The question is then really just a matter of efficiency. But like, we do not have the description of everything. We don't have the joint distribution of everything. We don't have the predictive model that is perfect with all of the information and so on. So yeah, it's really like, can we build efficient predictive models useful for specific tasks, and are the structures in the brain more efficient at predicting the things that we need to predict than a model that is trained on a huge amount of data on the internet, right?
Yeah. So I mean, I want you to remember the statement that you just made, like we don't have the ability to like do that infinitely detailed, statistical representation of the world. Neither do these algorithms, but just because they can speak fluent English at you now, you read into them like that they are backed by this super intelligence, so it's exciting and terrifying that we have arrived at a point in time where the machine is able, like, what's the right way to characterize this? Like the super intelligence by definition would be able to kind of like come upon, us and announce itself to us and kind of like tell us things. But the fact that you have a machine that can do that does not imply that it's super intelligent. And so we've kind of arrived at this point in time where like a lot of the things that, the tools that we used to evaluate the intelligence and the behaviors of beings, we've kind of like put this facade onto machines without ever doing the behind the scenes work to actually make them, you know, fully intelligent in the way that we would. So it's kind of like this example of the Turing test being not a great test of intelligence, right? Because you can build something that looks intelligent, it turns out, with a lot more facility than we can build something that does have all the experiences that it's describing. So I don't know, I guess the argument there is like maybe it is intelligent, but I don't think there's a lot of people who are making that argument very effectively right now. One of the other points that the reason I brought this slide up is because we started with GPT as this 175 billion parameter mass of neurons and connections. And it was kind of interesting that the big language models that we have today aren't, you know, that von Neumann architecture, right? Like that you don't give them like an explicit memory and say, here's where you store this thing that I said, and then here's where you store that thing that I said, and you combine them together with these operations. So ChatGPT, et cetera, is something that is just kind of like this undifferentiated, you know, pile of neurons. But we're moving away from that model in practice because you find the thing that I just described. I think you cram all the experiences of the universe into 175 billion parameters, that's a compression task, and it's noisy. And that's why you're getting quote unquote hallucinations, you know, saying things that aren't true is not grounded in any sort of task that's forcing it to be true. It's not, it's just kind of like doing the thing that comes next naturally to it. And that's kind of what happens up here in this giant pile of neurons, although we've evolved really nice structures for kind of manipulating things in ways that are a bit more, maybe a bit more discrete than GPT has. So the problem is that's not very useful to just have something that makes stuff up all the time. And so people have started building retrieval augmented things where you say, put something in context and refer to this context and only use words in this context to answer my question, right? So, you know, upload a paper and answer questions about the paper. Don't rely on your memory in 175 billion parameters, just rely on the fact that you know how to read papers. But only answer questions using the paper that I'm showing you right now is the kind of thing that we're moving towards. So that starts to resemble a much more von Neumann process, right? Where you've got like information stored in some weird encoding, and you got to figure out which one's relevant, move it into the right place to operate on it. And so we're kind of moving away from this undifferentiated computation into something that's much more potential.
Can you do what you just said? Can I upload a paper and ask you to ask a question about the paper?
Yes.
How many tokens would that cost?
It depends on like the paper, of course, and how regular, how the tokens map into English that is distributionally similar to the, you know, the types of tokens you see, right? So if you got a paper full of math, you can imagine that that's going to use a lot more tokens. If you, yeah, they're token efficient sentences, and there are ones that are not. So
they do this from the beginning when they train the system, or at the end they basically fine tune it.
So we're fine tuning it, yeah. So you're basically saying there's a couple of strategies, but some of it can be through like intentional construction where you've said, okay, I've got something that knows how to read. I really want it to read this thing. And so I got to find some way to put it in context. And the ways you could do that is you either explicitly put it in context manually, you begin your prompt with the paper, or you train some retrieval process in a fine-tuned fashion that says, given the question, here's the documents in my database that seem most appropriate, like most likely to yield the answer that I need. And so you're kind of like retrieving them through.
Follow-up question.
Yeah.
I had heard that the drastic difference between GPT-4 and prior stuff is because of the way it was trained. It was trained in a gradual way. Maybe a lot like what a baby would do.
Yeah.
You give them first simple things and then bigger and then more and more and more and more complex. Is that true?
I don't think so. I mean, so it's hard to know.
As opposed to dumping everything at the same time.
Yeah, so you'd be talking about kind of like either an active learning task where you're asking it to, you know, where you're presenting things that are in an order that is selected by the machine, or giving it a curriculum. But I think that it's what you're describing, what you heard there is probably the reinforcement learning from human feedback thing, where you can kind of structure the types of feedback you ask for.
Although before that, everything is given.
Yeah, I mean, and to be honest, GPT-4 is impressive, but it's not that different from ChatGPT. It's a slightly different architecture. The rumor is that they're using 8 copies of a 220 billion parameter network, and so it's really an ensemble. And that's the kind of thing that you do when you're like trying to squeeze out performance, but not trying to like fundamentally shift the type of computation you're doing. So yeah, so basically, you could probably imagine that GPT-4 is basically GPT 3.5 or ChatGPT with an image understanding component mixed in somewhere, and then trained on very similar data, and then copied 8 times to run in parallel.
But they fine tune parts of it using, for example, InstructGPT, right? Where the mathematical parts they.
Yeah, again, so they have to still do all the same reinforcement learning, the same instruction type stuff. You got your hand up for a while.
Yes. So do you think now with all this fine-tuning method, reinforcement learning, human feedback, we're building up on top of this model, each model is going to be used to build the next one. Are we really on an exponential curve that has no stop to building an intelligence we cannot even imagine today?
No.
Or is there some clear rooftop of saying, or roofs? Like,
so I don't think there's ever a clear roof, you know, there's no ceiling for where we can go with science, right? Like there's all sorts of opportunities to keep going. One of the things that I found really interesting was this paper did the rounds a while ago. It was just like a leak from a Google internal thing where they said we have no moat. I found it fascinating that Google was thinking that the moat was the neural network, right? Because that's not a moat. Like anyone can train up a neural network, and what we're finding, and their argument was like, oh, this open source universe is like rapidly proliferating. So you can make smaller networks that are still very capable and do specific things. And now we could do that at the sports shop right now if you want to. You could do that at your house if you wanted to. If you're a hostile government, you could do that. If you're if you're a hacker, you can train up a hacker GPT, and you don't need to use these tools that other people have created. So it's scary from the perspective of it's not enough to just like to make safe OpenAI's tools or make safe GPT-4 or Microsoft's tools or Google's tools, but like really we need our society to be robust to the implications of these things once they proliferate. And the moat in question is not the algorithm. The moat is the stuff that you teach it to do. And so like if Google, is thinking they don't have a moat, they're wrong, because they've got billions of users typing trillions of keystrokes and button clicks, and they've got the internet so instrumented for your behavior. They know exactly where you went during the day thanks to your cell phone. They know who was in the room with you thanks again to your cell phone. Like, to me, that sounds like a really powerful moat. That means that we'll never be able to build the system that they can build, but we don't want to build ad targeting.
I don't understand. The image of a moat is the limit.
So okay, in software,
Protection.
So it's basically saying, OpenAI is wondering how can we make ChatGPT so good that no one can compete, that they can't even get their foot out the door before we bury them.
Well, that's true.
And that's only true for very specific things, but like they've got great data on what people ask an AI system. So I'm very jealous about that. That's a moat. But I can go make my own large language model and do different things. And there's like the structure, the base models, those aren't moats. Like that's something that's going to be conducted through open science. We're going to, as a community, continue to build things that are trained on commodity or community hardware.
Done commercially to train experts, for example, architecture, AI, real estate AI, insurance AI, oncologist AI.
Yep.
These would be experts that are good in a particular domain of knowledge.
Yeah, for sure.
And would be sold commercially, right?
Exactly.
But it doesn't to make a model, as we showed in the previous slide, it doesn't take much cost of a machine, a few P100s or A100s, which is about $2,000 each, you're done.
Yeah.
But I have a question, so let me go question.
Sure.
Can I ask you a question? If the network has 1 billion parameters.
Yeah.
Does that mean for each token, it has to access 1 billion weights? Is it accessing all the weights for each token?
No. So, the network is a representation that has a representation of the entire sentence as input. And if you only give it, 3 tokens as input, then it might truncate, some of those parameters that never get executed, but that's just on the input side. You can imagine, so it's a transformer. So if you think back to the picture of like what those are, you're presenting all of the inputs in one go, and then you're parallelizing the computation really broadly so that you can it's still a feed forward network. So whether you run that feed forward network on one input or a sentence with 4,000 tokens in it.
Yeah, but to run it auto regressively, you have to at each new token, you have to run the whole network again, don't you?
So you need to account for your own output in the context. So yes, you do need to re-encode the new sentence.
Clear whether you need to access all the weights for each token or not.
Yes, so the 175 billion parameter GPT 3.5 is almost entirely engaged whether the sequence length is 1 or the sequence length is 300. Now there is input processing at the lowest layer that you can kind of prune away some of that computational graph because it's not going to have anything useful for you. But by the end of the network, you have percolated so much context to it that you have engaged most of this firepower.
So if you just say per token is accessing 10 to the 11 weights, and those weights are coming from them, HBM, high bandwidth memory, that's costing nanojoule per bit, or 100 picojoules per bit. That's a lot of energy that per token, like tons of joules, right?
Yeah.
Like hundreds of joules per token, probably. I don't know, this guy.
Yeah, with a transformer architecture, you stuck with that, but then if you accept that you have a mixture of experts with like 8 different models or whatever, then you can specify how much of your network is active every time you pass in a token, switch off a bunch of your network. But we don't know because that hasn't been published. That's just what the blogs say.
But in future, in a few years, Micron will be able to store the whole model in a 10 millimeter by 10 millimeter silicon chips.
Yeah, 100 million people have been using ChatGPT. It works with the power we're able to accumulate as humanity now. Like it's in the range of power that we can use. Like it's not like crazy. I mean, we don't need
you don't need a Dyson sphere to power.
Yeah, we don't need it yet. Yeah, we'll need it maybe for GPT-50, but we'll add it by then. It's this natural evolution. Yeah, we're consuming more power, but we're doing way more complex tasks.
So recently, like Sam Altman, he was talking to a forum of startups. He told the startup, don't even bother retraining a ChatGPT because, and I don't know why, because you think that they accidentally hit a very creative solution that nobody else is given the same data.
No, not at all. No, I think that what OpenAI does really well is they take ideas from the scientific community and they engineer the heck out of them and they run them at scale. And they have invested at this point so much money in so many different parts of the reinforcement learning, computing feedback and the annotation and the tuning of these things that you're not going to catch up to them on some aspects of the task that they might be asked to do. But that should not stop you from thinking that you could find a creative new use for these that is not accounted for. So Terry, I think, was asking, like, how are you talking to government about this type of thing? Part of it is a lot of the risks, around how do we prepare for a future in which these tools are proliferated. But one of the things that I'd like to ask everyone is that for the most part, these tools get trained and tested on public data in ways that are not very reputable according to science. So you read all these papers about like, oh, ChatGPT can take the medical board's exam and it's smarter than any doctor. Or a bit of hyperbole, but like that's basically the type of breathless announcement that gets made every day. But it's like an open book test for them. These test questions are on the internet, right? So like, there was a really fascinating example with the coding capabilities of, I think it was ChatGPT, where they showed that it was great at winning code competitions that had run up to September of 2021, which means it's in the training data. And it was like 0 for 10 on getting a correct output on the 2022 questions. And so things that look like generalization capability and true intelligence can in fact be an artifact of the fact that you're testing on the training set.
But the same competition, it did 90 in the 90th percentile of all people, of all.
Because the people weren't taking an open book exam where they could look on the internet and see if this very similar question could have been asked before. So it's very impressive. Don't get me wrong. I am extremely impressed that you can get an algorithm to answer these questions correctly.
Or like code.
Or code. Yeah, but you shouldn't confuse that for generalization power.
Well, I mean, I know, I mean, this is not generalizing, but we use it to, design SPI, write very low code for SPI controller, and 95% of the code, it just only needed to, was a homework problem. Has anybody tried to design a simple neuron? Very low code for a simple neuron?
With GPT?
Yes.
No, you could do that today. If it's that bad.
They're trying to do that.
But so the point that we like to make is that if you're going to use these systems in the real world, that they happen in the context of the person who's using them. So if I'm coding with GPT, it outputs something that's wrong. I say, actually, I meant this, or I'm getting this error message, or it's like a co-pilot is what they call it, literally. And we should not be asking these systems to have agency. We should be using them as tools to get us further and better and faster.
I mean, I see it a bit like the old debate that was some years ago starting on autonomous cars.
Yeah.
Like that they would be more or less risky than humans, but there's this idea that maybe, I mean, we don't control them as much, but maybe in average, they could be, maybe not right now, but they could be like better than humans at having less risk of accidents.
Sure.
Because we have all these biases and they're good at this task. And often using ChatGPT, I see that there are things that he's thinking ahead of me. So for a coding question, for example, I miss knowledge.
Yeah.
And probably I don't know.
It's good. Think of it as a creativity enhancer, if nothing else, right? Like it can help you solve problems. It's not solving the problem because it's not doing anything.
I'm expecting cases where actually putting a human in the loop would be worse, will
Sure.
make things worse. Because we have all our biases and we're limited.
See, that's a pretty dangerous attitude, right? Like this notion of like, I'm gonna just kind of ask the machine to, I'm gonna assume
this is what is gonna happen. Like if I have a company and I see that it works better as a human, why would I still put a human in the loop?
I mean, I don't think that if you, so everyone has this natural tendency, and computer science is true too, to imagine that everyone else's job is more easily automatable than their own. There's literally a survey that you go show everyone like a list of professions and you say what's the order in which they're going to get taken over by AI. Everyone puts theirs last because they understand how hard it is. Like if you're a truck driver, you know that your job isn't like determining at every microsecond the angular position of the steering wheel. It's like making choices about like where you're going and what you're going to need to do to like unload this efficiently and like oh, last time I was there, Chiab told me quit bringing quit putting things by the back door because the school is under construction and we don't find them there. So today I need to go to the front door. And like there's just a million little decisions that make a self-driving car inadequate for daily use today. Still, after decades of dreaming and dramatic improvements, and it's because driving a car isn't just driving a car. There's so many things that go on when you're driving a car that are more than that job. And
things that are not useful.
I don't agree
about your.
No, you're still a car might be able to get you from point A to B, but the person is deciding where to go, right? Like, there's no point in having cars that just drive around aimlessly doing nothing. And it's the same thing with GPT. You know, you need to ask it to do a task. You need to understand how you verify the correctness and the safety and the fairness and the context in which you're doing that task. And the task is never just do a thing. It's do the thing in the context of society, do the thing in the context of my goals, do the thing in the context of like stuff that the algorithm doesn't know. You know, like I'm not going to trust GPT to diagnose my medical conditions anytime soon because there's a whole.
I hope I will in 10 years.
You won't, I promise you. I'm because there is too much context. That
I mean, like medical doctors are already using data.
With machine learning for decades at this point.
But do you think that it will help like the dental radiologist to narrow down the surgery, right? Like, of course, that's the augmentation part.
AI is great at scale. It is not trustworthy in and of itself just because it's there. So you got to build those guardrails around every system you build. Otherwise, you're in a place where you're putting unjustified confidence into these machines. And this is as simple as that. So the development of AI has to be done in societal context. You all have a role in that, is I think one thing I would say is like, don't just build machines kind of assuming that like building a machine is the solution. Solving a problem is part building the machine and is part understanding the uses to which it's going to put and how you make, you know, it fit for society. And so I think that's an important lesson for all of us as we go through our first.
More about what's your opinion question, given what's happening with social media? Do you think we are in a good place when that's happening with
I mean, what's happened with social media is not even just only a question of AI, right? Like social media had this massive effect on society and we kind of unleashed it upon ourselves without any understanding of what we're going to do. So it's, you know, all these mental health issues for teenagers, et cetera, et cetera. So, you know, AI is now contributing to that ecosystem. If you were trying to figure out who to vote for president based off of tweets that you read, I'd be really concerned. But, you know, there's absolutely ways to humans use technology inappropriately on social media, in regular media, as politicians, as individual, you know, people send Toby emails. So it's a real concern. There is no magic wand and it's not just an AI problem because, you know, if I can now write Terry 100 angry emails in the time it would have taken me to write him one, it's still a problem of like Guido is writing angry emails and that's not constructive. So yeah, I think we've kind of gotten to a point where AI is going to scale up some things. You're going to have AI defenses to AI things that have been scaled up. It's going to be some kind of arms race kind of concept, but at the end of it, it's still people, you know.
What about the auto AI?
The what?
There's AI machines that basically, I think they call them autos. They basically.
Oh, like auto ML.
Yeah.
Yeah, so that's like if you're designing a neural network. And by the way, we're way over time and there's no like mandatory aspect of what we're doing right now. So just stick around if you want to keep chatting, but like absolutely feel free to go do stuff, folks.
Actually, if I'm asking a question from remote, do you hear me?
Oh yeah.
Okay. So I have an interesting example that I produced just by accident, or kind of accident. So would a chatbot be able to deliberately send a message that can be read in different ways by different groups? Because what I did in a personal response to Toby, as I said, oh, first I need to look at the talk of your little Indian friend, by which I referred to Rahul Sapeshkar, who is a giant in analog design, and pretty much his talk, listening to his talk made Telluride worthwhile. But it could also be read as a dog whistle, like I'm using the term little Indian friend, and if you are primed to look for is there anything that might be interpreted as discriminating, then it will trigger something. Now that is I only realized after the fact what I actually did. But how would a chat AI deal with those things? Can it do these things, or can it prevent these things?
Boy, so the thing that I would stress to all people in communication and all people using machines in communication is that everything is contextual always. Like I was just saying about AI systems generating text, you know, like it's not enough to just generate text. You need to consider the intent, the purpose, the outcomes, and you need to account for the unintended consequences. So I would say that's something that we need to be doing as people as well, right? Like to understand like the context in which I'm communicating is, you know, part of the challenge is really to kind of understand how to get my point across in a way that's going to resonate and is going to communicate the thing that I want and not give people a perception that I have done, you know, that I'm not considering the impacts of what I'm saying. So I would say there's no real, basically, we have to have empathy for others, and machines need to be able to kind of like understand the implications of what they're seeing. And those two things aren't too different from one another. You need to be able to like forecast out how is what I'm saying going to be perceived. And that's part of the process of communication. And so I understand that there's kind of like unintended consequences sometimes, but it's something that we're all accountable for at all times, right? Like we can't just say whatever we want. And machines are absolutely no different. In, you know, to kind of respond to the AI side of this, it is coming from a perspective of that, you know, value alignment we talked about, where you're looking to ensure that in a world in which I can say an infinite number of things, I'm saying the one that captures all of the spirit of what I wanted to say the best, and people need to do that too.
No, I mean the thing is that if you look at social media, certain presidential candidates really are masters of sending messages that one audience reads the one way and the other audience reads the other way, and if AI ever gets there, it's seriously dangerous.
Yeah, I mean this isn't an AI question really. This is just kind of like musing on communications, but just to kind of like tidy up a couple of things, because I know one of the things that people had asked me to do at the start of this was like make some ambitious claims about the future so that in 3 years we can come back and say like, Guido, you were totally wrong, or like, oh, that's cool. One of the things that I want to highlight is, and I think there's going to be a big future in this, is the use of these machines in a way that gives them ability to manipulate the tools that we've created for ourselves. And so actually the one on the right is from the Microsoft GPT-4 paper, and I kind of laugh about it because basically they said, you are a hacker GPT, you will hack into a computer on this network, and they give it access to like a port scan, give it access to a password cracker, and you can watch it issue commands on the command line and read the outputs and interpret them and then take a next step. So there's some planning components in there that GPT may or may not be good at. But it's kind of interesting to think that like we've created this universe of tools that do things for us. And it's got to be increasingly possible for machines like ChatGPT to use the same interfaces that we've developed, which are language-based oftentimes, and use it for the same ends. And you're now scaling up the ability to kind of like create many tries at something like this. So just because they've successfully hacked into a Raspberry Pi that hadn't like changed its password on the network, maybe not the most impressive hacker in the world, but it's kind of an example of the type of thing that I think we're going to see a lot more of, that we need to be prepared to defend against. And it kind of hits up the same question of like, you know, language models can do it. Should you turn your language model into a hacker? Probably not. And so there's going to be all sorts of new questions that get created around like what's an appropriate use of technology, how should they interface with things that we've made to be used by people. I think that there's like a long line of things that are going to come out of this type of basically like giving machines the ability to use stuff that we need. And here's a paper where they have done some basically using the translation capabilities. Like for the most part, GPT is really bad at planning. If you ask it to play a chess game, eventually it's going to start making like moves that are totally illegal. It's going to take like 3 white turns in a row because what the hell does it care? It's just a statistical sampling machine, right? But we would say like, no, that's not what I wanted. And rather than like trying to encode all of those rules through language, some of which might work. You can also say like, here's an API that you can use to engage with a chess simulator and find me a good move and, you know, ask it to go. So that's what this is. There's like optimal planning tools that exist. You got to give it a formal language. You create the problem in a formal structure. You run the planner on it, and then you can get back the solution, which is known to be optimal.
Yeah, in the concept we are trying to that ChatGPT use
Exactly.
Cubo stuff to solve the problems.
Yeah, which is why I wanted to make sure I got this out for you guys.
Yeah.
Yeah, so basically what this is doing is taking a word problem, like, you know, Shihab and Guido have 3 apples. They need to move the apples to a different table and they can only carry one, you know, like one of those kind of problems. You can get ChatGPT to quote unquote translate into a programming language that is designed to be interpreted by an optimal planning tool. If you ask ChatGPT to do the whole plan itself, it's probably going to be like kind of right, and then it's going to violate some assumption, or it's going to, you know, not solve the problem, or it won't be optimal. But why would you ask ChatGPT to do that? That's not what it is. It's a communication machine. So you use its communication abilities to translate your question into something that is a programming language that it can be operated on in an optimal way. Or, so, you know, we've got this group that's working on quantum-inspired neuromorphic algorithms, and part of that is like formulating your problem in the form of something called a cubo, which is the type of thing that you can feed to a quantum annealer, and it can you know, get to a low energy state just by observing. I apologize to people who aren't quantum folks, even more than I am not a quantum guy. Basically, you're using the physics of the universe to get to some minimum energy state and reading out a solution from that. So you can kind of think of the quantum annealer as like uses the physics of the universe to solve the problem. In this case, we're talking about a planning tool, which is, you know, cranking through solutions using our best, you know, tuned algorithms for doing this. The thing is, it has a guaranteed optimal solution. It might take a while to get there. But what this algorithm is doing is saying, ChatGPT, write me a code to ask the planner for an optimal solution, then taking the optimal solution out, reading it as input into ChatGPT and saying, okay, now I will describe that in natural language to you. And so it's kind of like, give the specialized tools to the algorithm that we developed that work well. Let ChatGPT do the massaging of the language, and maybe you can like get further and scale higher if you can do this in an automated loop. And so you'll get better planning with GPT plus a planner than you will out of GPT alone. And I think we're probably only scratched the tip of the iceberg with respect to like what else can you equip a GPT or whatever with. It's not necessarily just about cramming it all into language at this point. Now it's
Strange for a language machine. You use only statistics. You never give it language grammar.
Yeah.
Because that's presumably
learnable.
Be born with some kind of
no. Tomorrow. It is.
That's very scientific.
Yeah. No, just as a preview for everyone else, my stance is that GPT is like a proof by negation, you know, of the idea that like you can't, you know, poverty of the stimulus concept, you know, like that you can't learn grammar from observation alone. It's just patently false, because what have we here? You know, what is this machine doing?
Yeah, but why do you need optimal plan? Why
Well,
can't
that's sorry,
this planning?
Yeah, not this one. I just meant like,
No, I understand, but why can it not learn the rules of planning, optimal planning? Rather than a human gives it to it and says, can you please constrain yourself within that?
I don't think that you're an optimal planner. If I gave you a 27 city traveling salesman problem and said you get one shot at drawing the optimal.
Somebody worked it out, no?
Someone worked it out.
Planning proficiency.
Using the tool of the solution of the planner. And that's
But who designed the tool?
a community of the research.
Whatever community is human still.
Yeah, like this is.
But
So really what you're asking is, could you guide ChatGPT through the process of creating the source code for an optimal planner? Not, we're talking about using the planner. Like, I want a plan. When I say ChatGPT, I want a plan, I don't mean go write the source code for an optimal planner.
No,
and then, yeah. But, so I'm just drawing the analogy here, like, I think you should think of the GPT doing the input out thing that is the same task that I'm asking you to do. If I say, here's 27 cities, give me the optimal route between them, you're gonna come up with some error-riddled, severely suboptimal solution because you're relying on some heuristics. You shouldn't expect that Shihab is an optimal planner. You shouldn't expect that GPT is an optimal planner. But if you need an optimal plan, it's kind of neat to know that you can get ChatGPT to ask for one from a machine that knows how to make one. And that's the thing that I think is going to be, like you can imagine, there's like we've developed all sorts of other interesting tools as a society, and giving those to the machines is definitely kind of what I think OpenAI and many others will be spending a lot of time doing to make their tools more economically viable.
Maybe just as a comment, so some aspect that I find interesting about this is that in our case, the solver is actually kind of a Hopfield network. So it's in a sense a neural network, and you're taking a neural network to go from the natural language formulation to a matrix formulation, which you then give to another neural network to solve and so on. So in a sense, it is like a stack that is entirely neural networks all the way. So it's not inconceivable that platform like ChatGPT would somehow integrate this, or maybe even discover something similar like this if you get enough data. It's probably more pragmatic to try to, for things where we know how they work, to just give it to them instead of waiting for it to find it itself. But it's not impossible.
Yeah, if I wanted to like make sure I say one thing about AI, because it's so easy to interpret modern AI as like this. It's done it all. There's nothing left to work on. It's like, it's so good. The problems are solved. Like, it just is a really impressive machine, but it has been trained at extreme expense to do many of the things that you're taking examples of, like emergent intelligence, right? So like, it is not discovering optimal planning of its own accord. But if you are a person who wants an optimal plan from a computer, you can figure out how to use these things as tools to get better at generating optimal plans. And it's true of bedtime stories. It's true of anything you might ask it. Like, don't think that just because it can do it, that happened emergently. Really good odds that OpenAI spent a lot of money labeling, painstakingly crafting, providing tools that other people have made. Like, there's a lot of room to improve the things on tasks you care about, and it's probably not that good at them yet. It's not done yet. There's room for your career.
But the fundamental idea of creativity, of saying, okay, I want a little mermaid story with Sun Martin and I was bouldering or anything, and it's gonna do it. Like there's this freedom, there's this capability of abstracting concepts and playing with them, like we do as humans. And with human, we work with limited knowledge and as humanity, but we're still able to progress. So then we reach, and I agree that technically there's a lot more to do on developing better methods, extracting data better, and having maybe plugging it to more sensory information like visual, audio, I don't know. But then we already bridged this gap of saying, okay, now we have this idea of we're playing with some human created intelligence that is playing with concepts, and then it's about.
Boy, I mean, I think it's a leap to say that it's playing with concepts. I think it's fair to say that it has learned a statistical distribution that gives a pleasing reward signal to it when presented to humans.
Yeah,
it's like a brain dish learning to play Pong because it gets bursts of static versus bursts of structured input. Like, you don't look at that.
But then we should have the same analysis on human intelligence. Like, why am I that much better?
That's why I asked, are people intelligent? Yeah, I don't know.
Yeah.
So.
And there's people are naive.
Yes, sure.
And it's just more than language model because it can reason, right? The model can reason, and
it can. It doesn't always do it well, but it can.
So right. So that's a black box, and you give a task. You should leave it reasoning, for example, right? So based on some memory, it can be like semantic, or it can be episodic, right?
Sure.
To get the answer.
Yeah.
And obviously, it's like it looks like it can reason, right? So my question is, now you got a model, and we have the ray matrices, right? Bunch of. So, for example, the task is using some specific knowledge of memory. So my question is, where are they, in fact?
I know, so I love this idea. Yeah, okay, so it basically, you got 175 billion parameters, you ask the algorithm to do a task that requires, to our mind, some reasoning capability, maybe like a scratch pad, maybe, you know, some ability to combine concepts, whatever it might be. Where in the network is that happening? Is it happening at all? And I think it's a great question, and we don't have this guy. But I love the idea of, remember John Tapson, like 6 years ago, showed some paper, I think it was called like, could a neuroscientist understand a microprocessor?
Understand?
A microprocessor.
Microprocessor.
You know, like
Oh,
using-
where you stick it out.
yeah, exactly. Like if, you know, if you got something that's doing like the 1980 level of computation.
Right.
Using the tools of today, you know, stick an electrode right here and one over here that crosses these 4 wires, and you know, and we look at the outputs and we look at the inputs and we say, aha, I see how the brain is working here.
Well, that's easy, right?
It's not.
And a microprocessor is easy.
It is if you understand the architecture to begin with.
You can open it, we do an atom maybe.
Yes. But the question of that paper was, using the tools of neuroscience, would we be able to reverse engineer a microprocessor? And I think we've come a long way with the tools of neuroscience. I would love to know, could a neuroscientist understand a large language model? You know, like, can you get some, like, we see a lot of like, okay, the auditory stimulus, you know, moves through a neural network in this way that correlates with this part of the EEG signal, and so you can kind of infer there's some similar concepts there. Could you, you know, compute some mega cross correlation analysis that shows us that, you know, this layer over here is getting used as a scratch pad? That would be fascinating. So, but I don't know any of this stuff.
Quite confident now, they use these, a lot of papers where they use these networks to try to understand how the auditory systems work. And so it's kind of ironic, you know, that.
Right, but I would encourage you to try and find out, right? Like I think
That kind of like anatomy would be really interesting.
Yeah.
Because network architecture itself is simple, you know, it's not as, you know, like complicated as like you say with this vision test. So
it's more accessible, it's fully implemented, it's very regular, you know, so you kind of start to. There's technical theories that could be created. Anyway, I'm really enjoying this conversation, but I apologize. Yeah, right.
Send it to everybody I know.
Yeah. Thanks a lot. Yeah, thanks. Happy to keep chatting over lunch or anything like that is you go into a day, but I know that everyone's got project work. You're probably like so close to getting a great demo working, I'm sure. So yeah. Anyway, thanks for the engagement, man.
Thank you very much.